So let's go over this June 2016 Chemistry Regents. Now, unlike my other videos where I have these annotations that will link you directly to the question, because YouTube has gone away with annotations, I no longer have those, but what I do have below, if you click under the Show More button, you can click to the link that'll take you directly to each question. The best way to view these videos and to really review here is take this test. Grade it with the key provided by New York State, or look through the video in its entirety, which I'll play for you. But the best way would be to take the test, then with the ones that you've gotten wrong after you've graded it, okay, go over the ones you get wrong. Fix what you get wrong, and then, my friends, in chemistry, okay, take another one and fix what you get wrong, and that way you will improve. So any case, again, if you want to go to the question, exact question on this test that you had trouble with, click on the link below, click on the Show More under the description, and it'll take you directly to the question you want. If you want to watch it in its entirety, well, let's begin. All right, so let's be crazy and go in order, and starting with number 1 of the multiple choice. So which statement describes the charge of an electron and the charge of a proton? So normally in this test, in number 1, we love to start, or at least these tests love to start with atomic structure. They tend to stay in order of some sequence of units. So to understand the beginning part, it's going to be about usually protons, neutrons, electrons. Even you're going to get some nuclear chemistry because it's about the particles. And anytime you get questions about particles, okay, the best way, if you're going to compare particles, if you're unsure, is go to Table O. It is one of the most underutilized tables, and most people don't teach Table O with this area of chemistry. So in any case, the charge of an electron and the charge of a proton. If you didn't know a proton was +1, if you didn't know an electron is -1, Table O is your friend. But let's assume you knew that. Let's go through the choices. An electron and a proton both have a charge of +1. Of course not. Okay? Electron and proton both have a charge of -1. No. And the reason why 1 and 2 really don't work is because when you say the word atom, I want to say neutral. So say atom. Neutral. Atoms always equal neutral. Why? Well, that's atoms. The protons equal the electrons. And if the protons are positive, electrons must be negative, because atom means a neutral, okay, particle. They have to equal themselves out. So electron has a charge of -1 and a proton is a +1. You probably knew that, but if you got this wrong, okay, that's why you're choosing this question. Let's go to Table O to show you where you can pull this information from. Okay, so let's do that. So Table O, my friends, gives you the particles. Like nuclear chemistry, well, these are the types of chemistry or physics in the particles that we deal with. So proton, you will see the particle 1/1. Okay, sometimes we call a hydrogen ion a proton because a hydrogen, okay, is a proton with an electron. If it's an atom, a hydrogen atom, if you lose the electron, it's just a proton. So the top number is the mass number, and the bottom number is the charge number. So the charge of a proton is +1. Now you say, well, where's the electron? Well, a beta particle is essentially an electron. And you should know that. In the old reference table, they used to write that. Now they want you to know that? I'm not sure. But they put a mass of 0. Sometimes they ask for those things. And of course, the charge is -1. Now, in truth, electrons do have some mass. They're about 2,000 times lighter than a hydrogen or a neutron. Notice the entire mass of the atom, due to something called the gold foil experiment, is due to the mass that's found in the nucleus, and the nucleus is neutrons and protons. So look, neutrons have a mass of 1 and they have no charge. So you can look at the particles here, party people. Beta particle is an electron, neutron is here, and a proton. Yes, we have our other particles as well. So beta particle is essentially an electron, high-speed electron. So let's get back to the question. So the answer is choice 4. Electron is -1 because of the particle written. If you didn't know, there's a -1 charge, and a proton is a charge of +1, as written from Table O. Okay, I like saying Table O. Okay, like you're from Brooklyn. Oh, okay, any case. you've got the charge of +1. Again, if you got one wrong, okay, the table O is a place to look. Now, of course, in table one, in question 1, they could have asked you about a neutron as well. Mass of 1 and a charge of 0. They love to compare these guys. Okay, even though the neutron wasn't part of the problem, if you got one wrong, okay, or number 1 wrong, they could have easily asked about that. All right, again, if I'm over teaching this question, go on to the next question. Number 2. Which subatomic particle is found in the nucleus of an atom of beryllium? So what's in the nucleus? As I mentioned in number 1, okay, in the nucleus, because of the gold foil experiment where Ernest Rutherford, or at least Ernest Martin and Hans Geiger, those people that were under him actually did the experiment, they shot alpha particles, which we now know are helium nuclei, okay, 2 protons and 2 neutrons, and most of these guys went right through. And when they got close, they deflected away, meaning that the nucleus was positive. And sometimes when they really got close, they almost bounced straight back, but most of the time they went right through. Atom is mostly empty space. We found from this experiment that the nucleus is a small part of the overall volume of the atom, and that all the mass is located there. So who has what particles have mass? Well, if you look at table O, okay, you have a proton and you have a neutron. So these guys sometimes are called nucleons. So the mass of the atom is due to the protons and neutrons. They said an atom of beryllium, but it could have been any atom. All right, so the nucleus of the atom has the mass. Now, there's really no place to get that information from. That's something you have to know, that the mass of the atom is from these 2 particles, okay, and that these 2 particles are found in a nucleus. That's a concept level question, okay? So that is very important that you understand that the entire mass of the atom is due to these 2 particles. Notice electron is given as 0. Now I'm looking at values given to me in table O, all right? So in any case, choice 3 is the answer. Okay, moving on to number 3. Elements in period 4 in the periodic table are arranged according to order of increasing what? Well, if you look at the periodic table, okay, you may have learned that the early periodic table, Dmitri Mendeleev put the periodic table in order of atomic mass because they only had mass. But later, okay, Henry Moseley with his X-ray experiment reordered the periodic table just a little tiny bit, a couple of them in order of atomic number. It's a periodic function of its atomic number. So in our periodic table given to us in our reference tables, we have atomic number 6. They give you this little key, and this, of course, is the proton number. And you notice they all go in order, and they're arranged in order of atomic number. Okay, and that's something you could look up and do. It's something that's also a concept type question, but it's arranged in order. You won't find anything going out of order. Okay, the atomic mass, however, does go out of order. Okay, and there are couple examples if you look closely at cobalt and nickel when they rearranged the table a little bit, when Henry Moseley figured out that different atoms differed by different number of protons. Look at cobalt. These guys are actually in these 2 positions because they have very similar properties. Notice atoms are placed based on their properties. Notice cobalt's 58.9 and nickel's 58.6, so it doesn't go in order of atomic mass. It originally was, but now it's about atomic number. So number 3 is 2. Number 4. Which phrase describes 2 forms of solid carbon? Diamond and graphite at STP. Well, if you've been around with me long enough, you know that when you have 2 different forms, that is meaning you have 2 different structures. And as I will say over and over, especially in organic chemistry, and this is carbon-based, but structure is king. Say it with me, structure is king. You change the structure, you change the properties, physical and chemical. So they're going to have 2 different forms. So therefore they're going to have different structures, different crystal structures. And if you have different structures, you will have different properties. Okay, just like you had in AP biology or living environment, when you have enzymes of different forms, they will have different, okay, functions or different um, active sites. Okay, so very important. Structure is king. Change the structure, you change its chemical and physical properties. Now that's not listed here, but that could easily have been a question, okay, in this Regents or in this area. Okay, so number 4 is choice 4. Number 5. Okay, number 5. Which element has 6 electrons or 6 valence electrons? Okay, in each of its atoms in the ground state. Couple of things we have to understand. Ground state means we're in the lowest energy for an electron. Now, what's the opposite of lowest energy? Well, high energy, and that'd be an excited state. Okay, so we're talking about electrons that are existing in their lowest possible energy states. They're not excited, which means they're not jumping to higher energy levels. Now, valence, another important term here, means that these are the outermost electrons. These are electrons that are available for bonding. They're not as stable. And what goes with valence, just like you have ground state, the opposite is excited state. And again, not part of the question, but something you should be aware of. The opposite of valence would be kernel or core electrons. These are electrons held closer to the nucleus. Valence electrons are held farther away, and they're more unstable as they're farther away because they feel the nucleus less. Remember, the nucleus is positive, and if electrons are held closer, they're going to feel that positive more, and they're not able to move as much. Electrons that are proximity-wise farther away feel the nucleus less, and they have higher energy. So if electrons are in an excited state, they're in places where they don't belong because they absorbed energy. They belong lower. But we see ground state, all the electrons are in their lowest energy positions, as close to the nucleus as possible. Now we're looking for valence. Valence is those outermost electrons, and they're looking for 6. So the best way to do this is go find what column. Remember, columns on the periodic table are called family of elements, and they're based upon similar properties. And their properties, remember, if you're in the same family, you have the same properties. Maybe you're all tall, dark hair, all good looking, who knows? The problem is, in elements or atoms, how do we know they are similar? Well, in the same row, it makes them similar is not because of hair color, eye color, it's because of the same number of valence electrons. So if you have the same number of valence electrons, you have similar chemical properties. Now we draw Lewis dot diagrams with dots to show, okay, as many electrons that are available for bonding. So this could be element, let's say X, who knows what it is, but we would show it with 6 dots to show that there are 6 valence electrons. And as we've done before, it either gains 2 or shares 2 more, depending upon if it's covalent or ionic, to fill its 8. 8 is that magic octet. So who's got 6? Gallium, krypton, selenium, or arsenic? Let's go to the periodic table. Well, looking at my periodic table, looking at group 16, if you take the 1 away, they all have 6 valence electrons. A little trick, how do I know? Look at oxygen, it's 2-6. If I rewrite it up here, that's the configuration. There's 2 electrons in the first energy level, okay? And there are 6 electrons in the second energy level, or the second shell. So these electrons are called the kernel. Those are the core. They're stable. They're closer to the nucleus. Think of the nucleus as this positive thing right in front of the configuration, and these guys are farther away, and they get stable when you fill them, and filling the second energy level would be 8. Okay, so wow, we need something to be 2-6. Well, look at this. They all are to have 6 in the outermost. If you're in group 16, take the 1 away, it's 6. So look at this. Selenium has 6 outermost electrons, and that's why selenium is the answer. So choice 5 is selenium. Question 5 is choice 1, selenium. Number 6. So number 6, what is the chemical name of this compound, H2SO3? And they're all acids. And when you first look at this question, when I first look at this question, I think, oh my gosh, they have to know how to name acids? Okay, when in fact you do not. In fact, if you do know, if your teacher did teach you, this is the sulfite ion. SO3 minus is the sulfite ion. You can look that up in table E. I call table E, what the heck is that? Cluster of polyatomic ions. and ites become OUS. So that'd be sulfurous acid. Okay, and that's why choice 2 is the answer, but you do not have to know that. All they're asking for really in this question, they're asking is, do you know where to look for the name of common acid? So H2SO3, if you go to the periodic table, or I'm sorry, table K, there it is. There's a list of common acids in table K, and that's all they're asking you to do. Do you know there's a table called table K that lists common acids? And do you know to look that up? Because it's not part of the curriculum to know how to name acids. If you were to name this IUPAC name, this is hydrogen sulfite, and SO3 is listed in table E. So all it was saying is, do you know that there was a list of acids and the names are given to you? So it's really a straight reference table question. So again, number 6 is 2, not because you have to know how to name the acid, but because of just looking up where the common acids are listed in table K. All right, so number 7, let's go on to number 7. Which substance is most soluble in water? Now, soluble means that we're going to make a solution. And then we make a solution, it's going to make an aqueous phase, if you want to call it that. It's going to dissolve in water, it's going to interact with water, it's going to have similar attractive forces, and essentially water is going to be able to break apart all of these ionic compounds. And how do I know these are ionic? Well, first of all, if I see a metal involved in a compound, that screams to me that we're dealing with ionic compounds. They are positive ions, and then what they are bonded to are negative ions. And these clusters, okay, these clusters of nonmetals are polyatomic ions listed in table E. Table E is, what the heck is that? Now, what's interesting in number 1 is that we have a lot of clusters. This is a -3 cluster. This is a positive cluster. Okay, so when you see a group of nonmetals and you say, what the heck is that? That's a table E type of identification. But this question really isn't about table E. They're saying what's more soluble, which means which ones break apart easily in water? Which one can water basically compete with the charges? And what I mean by that is, if I have something positive, it's attracting something negative. And then let's just get rid of some stuff here. Then it's going to attract something that is also negative and positive. Now, what I mean by that is, if I take, again, let's do the red, because we're staying in a red motif, I guess, and this is negative, and this is positive, and this is what happens in ionic compounds. Because you're negative and positive in all directions, you can attract other opposite ions in all directions, and this is how you build a crystal lattice. Now I'm just drawing it in 2-dimensional, but it comes out of the page and into the page. So this is an ionic compound, and you learn that ionic compounds are always empirical. The chemical formula of these guys are the lowest ratio of ions. But getting back to that, how are they most soluble? We're going to go to the periodic table, but you have to understand the concept here. See, water's got a negative side and a positive side. Water is not ionic. It's a molecule. It's a molecular compound made of nonmetals. And this negative side is going to surround, okay, let's say this positive ion, the oxygen end, the more electronegative end. And if the negative end surrounds, we call these molecule ion attractions, what's going to happen is this positive ion will no longer feel the attractive forces of these two negatives, and the water will basically pull this ion out, and that's what happens in dissolving or hydration, okay, or dissolution, all fancy names for the same thing. So the bottom line is, why can water pull some part, not others? Well, it usually depends upon the size of the charges, but we don't have to know the solubility rules. We have a table that does it. So we have table E that talks about polyatomic ions, but then we have table F, or as I like to say, table foo-foo. Okay, let's go there to see which one is more soluble. Now we have ammonium phosphate. These are the IUPAC names of these polyatomic ions. Copper hydroxide. Now copper is a transitional element. It has multiple charges. So this would be copper 2, this is -2 overall, so this is copper Roman numeral 2 hydroxide, silver sulfate, and calcium carbonate. So let's go through our choices to see which one from table F is the most soluble. Okay, so yeah, they didn't say it, they didn't say go to it, but it's really a table F question. Again, I'm teaching you the concepts behind it. So let's go to the table. So table F, this is the solubility guidelines or rules. So in any case, I want to see who's soluble. So who are soluble? So well, let's see here. We don't see our compound. So the first compound we had was ammonium. That's the ammonium ion. Phosphate, PO4. It's the PO4. Okay, and because PO4 is, of course, -3, I would need 3 of these. Okay, so guess what? Anything with a phosphate, look at this. Let's go find, are insoluble, but there's an exception, and that's with what? Ammonium ion. So ammonium phosphate is soluble. Oh, look at here though. Ions that form soluble compounds, if you have an ammonium ion, hey, we do, they're always going to be soluble, no exceptions. So no matter what rule you take from looking at the phosphate, who normally isn't soluble because of the high charge, and there are some exceptions, and ammonium is with them, so this would tell us that phosphate is not insoluble, it's soluble. Or looking at the ammonium ion itself, seeing that it's soluble, okay, it's going to be, and there's no exceptions to that, so just having this ion tells us that that is going to make a soluble compound. Water is going to be able to get in there and break this ionic crystal up. Now that's why that's the answer. Now if you look at our other choices, we had copper hydroxide. Now we don't have copper anywhere here, but here's our hydroxides. They're normally insoluble. Okay, it doesn't have a high charge, but it's a very small ion, so that's kind of reasons why there, but not part of this course. When combined, there are exceptions. Okay, so hydroxide is normally insoluble, and is copper an exception? No. So copper hydroxide is insoluble based on these rules, and they're looking for the most soluble. The other choice was silver sulfate, and silver sulfate. Okay, let's go find sulfates. Sulfates, ooh, they are soluble. But if you look carefully here, oops. So if you look carefully, sulfates are soluble, except when you have silver, and we do. So silver sulfate, okay, is insoluble. And of course, an insoluble means that if this was made through a double replacement reaction, that would be a precipitated, be in the solid phase. It wouldn't dissolve, but this is insoluble, so it's not the most soluble. Water cannot compete with these ions in the crystal. And the last one is calcium carbonate. Well, look at carbonates. These are insoluble. Is calcium an exception? The answer is no, so therefore calcium carbonate is insoluble. So therefore, the one that is the most soluble is the one that shows us solubility, okay, and that's why ammonium phosphate is the answer. So number 7 is 1, ammonium phosphate. Okay, and let's go on to number 8. Number 8, which type of bonding is present in a sample of an element that's malleable? That is the key word, malleability. And essentially malleability means we take a mallet or a hammer and we can basically shape this substance into almost any shape. It has the ability to take on any shape. We can hammer it into a thin sheet, okay? And the reason that we can do this is because it has certain types of bonding that allows it to take on any shape. Things that are covalent, whether it's polar or not, are fighting between electrons. For instance, if you see iodine, who has 7 valence electrons, it will bond with another iodine who has 7 valence electrons, and by sharing they both feel like they have the 8, as you have done so in your great chemistry class. But because their electronegativity is so high for nonmetals, remember nonmetals are the smaller ones. As you go right across the periodic table, the atomic radii get smaller because the ability of the what? Protons to pull in the electrons increases. And if they attract electrons pretty well, and they're able to attract other people's electrons very well. We call that electronegativity. So nonmetals above the staircase, and iodine's an example, are pulling on these electrons. They're both pulling very tightly. So these electrons are being tugged in both directions. They're being fought for. It's like a tug of war and nobody wins, so it's like a stalemate. Sometimes they win a little bit on one side, and we call that a polar covalent bond. Here it's a nonpolar because they both have the same electronegativity, but both of these are not malleable because if you apply a stress to these atoms that are fighting for these pairs of electron, you'll wind up cracking that bond. And so you should know things that are covalent, okay, are normally very brittle because of their fight for the electrons. And they're called molecular compounds because they make an exact shape. So molecular compounds that make molecules are covalent. These are important terms. You have to know it in this course. This course is about covalent versus ionic a lot, or metals versus nonmetals. That's the major theme. So we get rid of this. Malleable means we have a metal, and you should know that the type of bonding that exists between metals alone is called metallic bonding. That is your answer. Okay, and the reason why this works is if you, let's say you have copper and you have a copper nucleus and it makes a crystal lattice like an ionic compound, but the difference here is that the electrons are loosely held. Remember I says you go across to the right, the atomic radii gets smaller because the nucleus has a greater ability to pull in the electrons. Well, if you go to the left and down, atoms get bigger. The electrons are even more loosely held. And if electrons are loosely held, what can happen is that we can have electrons that can actually move throughout the crystal lattice of a metal. And we call this a sea of mobile electrons. And if you think with me for a second, if I apply a stress like a hammer to this compound, okay, because all of these nuclei that are positive because of the protons are attracting electrons in all directions, and they're attracting everyone else's electrons, okay, they're not going to cleave and stress. Think of something non-polar covalent or polar covalent as someone that's like OCD, really crazy for electrons. If you apply a stress to them, they're going to crack a little bit. Here, these guys, because they attract in all directions, applying a stress in one direction won't make them break because they're attracting electrons in all directions, okay? And that's what malleability is. Now, ionic compounds are not malleable, and why that is the case is because we have a positive attracting a negative. And if you apply a stress, now these aren't, the electrons aren't free to roam. Electrons valence wise were lost or gained to make octets. So it's not about electrons traveling. So you have these ions here. Now if you apply a stress, let's say a hammer, and you push this ion, okay, closer this way, well, what's going to happen? This positive and this positive repel, and basically you're going to have a cleavage. You're going to have cleavage, and what that means is you're going to be able to break this thing. So that does not work for ionic compounds. Number 8 is 2. Malleable is a property of metals, and metals, when they bond with themselves, are called metallic bonds. Okay, and it's the same reason if they use the word ductile. Ductile just means that you could basically shape this metallic substance, a sea of mobile electrons, into very thin wire. Can't do that with molecular or covalent. They're brittle, they would break. Okay, so number 9. Number 8 is 2, number 9. Number 9, which atom has the greatest attraction for electrons in a chemical bond? This is an important understanding. Greatest attraction, fancy word, is electronegativity. Get that down. Electronegativity. Now, who has the greatest attraction? Well, What I know from the periodic table as I go across the periodic table, the atoms get smaller because the ability for atoms to attract their own electrons increases. So remember, protons are positive, electrons are outside the nucleus, but as the nuclear charge as I add more protons, I'm able to pull these electrons on the outside closer. And if the charge of the nucleus, number of protons, increases enough that I can pull my own electrons in, therefore I have a good ability to attract other people's electrons and pull them in. So essentially, as I go across and up on the periodic table, my ability to attract electron increases. Now, in this problem, they give me hydrogen, oxygen, silicon, and sulfur. So these guys, okay, are not all in the same row or in the same column, so I can't use my understanding of the trends in the periodic table. Now, even if I could, I can always answer a question like this based on a table, and I probably call this table the most underutilized table, and it's Table S. Table S gives us electronegativity values for all of the atoms. It gives us the names, it gives us the density, the ionization energy, melting points. It gives a whole bunch of information that sometimes we forget. So really, to answer this question, and you have time in a 3-hour test, you could look up the electronegativities of these 4 elements. Now, I know something, that oxygen is right next to fluorine. Okay, and fluorine is the most electronegative atom. Oxygen is second best. Since fluorine's not there, I know the answer is oxygen. But if I wasn't sure, okay, I can go to table S, and let's go there to show you where to look this up. So here we are with table S in all of its glory, and let's look at hydrogen, electronegativity, attraction for other people's electron, 2.2. Look at oxygen, 3.4. That's the winner that I think is going to be. And silicon, as I go down, all this information is 1.9. And if I go to sulfur, which is under oxygen, is 2.6. So the winner is oxygen. And that's why that's the one that is the most electronegative. Now, you had to know that this means the attraction for other people's electrons. That is going to come up. Okay. All right, notice ionization energy, another trend they could ask for. This is the energy it takes to pull an electron away. All right, but look at all the stuff they give you. The symbol, the name that goes with the symbol, melting point, boiling point. Density is the one that pops up and creeps up sometimes, where you need to know this value, and it's given there. And of course, atomic radius, the size of the atom. Okay, moving on. Number 10, which type of reaction involves a transfer of electrons? Well, transfer of electrons means that someone is losing electrons and someone is gaining electrons. That should ring true to you. Losing electrons is Leo. Losing electrons is oxidation. Gaining electrons is reduction. So it's oxidation reduction. Neutralization is where you're losing and gaining protons. Remember, acids give off the H pluses and bases. Double replacement is where we have positive and negative ions from two aqueous solutions, and all you're doing is what? Switching partners. This positive goes with this negative, this positive goes with this negative. And alpha decay is that scenario where we have, let's say we have radon 22286 give off an alpha particle from table O, which is a 4 He. It's a helium nucleus, 2 protons, 2 neutrons. What number plus 2 is 86? That's 84. What number plus 4 is it? And that'd be what number plus 4 equals 222, and that's 218, and this would be polonium, and that gives off an alpha particle, and that's a nuclear equation. That's basically losing protons and neutrons. Okay, has nothing to do with electrons. Nuclear chemistry has nothing to do with electrons. Okay, so moving on to number 11. Okay, number 11 gave people some fits. Let's go over it. A 10-gram sample of nitrogen is at STP. That's key. Now, standard temperature and pressure. Of course, standard temperature is 273 Kelvin, which is equal to 0 degrees Celsius. Standard pressure, is 1 atmosphere. Easy for me to say. Which property will increase when the sample is cooled to 72? So we're going from 273 to 72 Kelvin. We're getting cooler. Well, guess what? Temperature is decreasing. Okay. Um, Volume. How do we answer this? Well, how do we answer density? Well, there's a key to that, but we do know we can get rid of probably mass. Cooling something will never make it lose its mass. Only time we can think of mass being lost in a temperature change is possibly a liquid going to a gas in evaporation. But here, just cooling the sample, if we already have 10 grams of it at 273, will not change the mass. The question is, how do I know its volume? How do I know its density? And this is one of those questions where you need to understand that Table S, one of the most underutilized tables, can give you some information. Table S is going to give us phase change information about nitrogen. So let's go there to see what's happening at 72 as compared to 273. All right, so let's go find our nitrogen. And what do we know about nitrogen? Well, look at this. Boiling point is 77. What does this mean? Well, that means that's when the liquid, okay, is maximally evaporating into a gas. So that means anything above 77, we have a gas phase. Now, if you don't like any of that, okay, if you can't see that, let's do a little heating and cooling curve here, right? So if we did a little heating and cooling curve, what do we have? Well, we have this idea of a liquid, make this the liquid phase, and then we reach that temperature where the phase change occurs. Liquid is going to a gas. That's where the kinetic energy is being converted to potential. And then we have the gas phase up here. Okay, I say gas because gases have tremendous potential energy and a tremendous kinetic energy. There's no limit to how high they can get. So this is occurring at 77, okay, Kelvin. And of course, kinetic energy is equal to, the average kinetic energy is equal to temperature. So anything above 77, as you can see, anything above this temperature is in the gas phase. So at 273 Kelvin, which is at STP, they said you had nitrogen. If we heat it to the temperature that they talked about, which was 72 Kelvin, my short-term memory is gone at this height. So they said that we're heating it to 72 Kelvin. So 72 Kelvin, let's say, be somewhere here. So that means that we're going to go from a gas to a liquid. And we know that gases have less intermolecular attractions and take up more volume than liquids who are closer together, and guess what, are more dense. So when a gas goes to a liquid, basically by giving us 72 and starting at 273 and using table S, and they're not telling you to, you have to know that this is available. They're basically saying that condensation is occurring, and if condensation is occurring, then the gas is becoming a liquid. And if a gas is becoming a liquid, okay, the molecules are going to be closer. Gases are far apart, liquids are closer together, and the density is going to increase. The mass won't. All these particles now become a liquid. The temperature is decreasing, okay? So it's all about the density increasing. The volume is going to decrease. For the same amount of particles of a liquid, a gas will take up more volume. So the only answer that's increasing is the density, the amount of mass, because you have more particles, and so you're going to have a lot more mass for a smaller amount of volume. That's going to give you a higher density. Okay? So number 11 is 3 densities and going to increase. Okay? Density is increase. And number 12, who's a gas at STP? Okay, And xenon is your answer. And if you don't know, one way to know this is go to your periodic table. Call this, to find my gas, the LL rule. If you put an L on your head to show that you are a big L, it'll be a backwards L. So basically it's a backwards LL rule. But in any case, if you turn this on its side, okay, you'll get here and all the way down are gases and naphthol. So all of these are gases. And of course, these are my two liquids and the rest are solids. That's how you remember all your phases at STP. Notice krypton is my gas, xenon is a gas. All these here are my gases. So if I go back to my problem, you'll see that xenon, the noble gas, of course, is the one that's a gas, and that's why number 12 is 2. Number 13. Number 13, a 5-gram sample of iron is to be placed in 100 milliliters of hydrochloric acid. Which changes result in the fastest reaction rate? Okay, so what are the factors that affect a reaction rate, how fast a reaction goes? Well, when we talk about how fast a reaction goes, what we're really about essentially which of the factors will increase the frequency of collisions. Now, why do I care about the frequency of collisions? Well, if I have my reacting molecules, in this case, an iron atom and a molecule of HCl, okay, when they collide, okay, if they collide more frequently, there is going to be a higher amount of effective collisions. You should be aware that an effective collision is a collision that has a high enough kinetic energy in both of these particles so that they overcome their repulsive electron clouds. And if you're not sure why we need that, that's called the activation energy. We need enough energy, okay, to overcome this barrier to the reactions, this activation energy, okay, to happen. And we have to have proper orientation. Sometimes only certain parts of the molecule, okay, reacts, okay. So in any case, so if we increase the number of collisions just by pure chance and statistics, we're going to increase the number of effective collisions. So how do we increase the number of collisions? Well, some easy factors, okay, and if you look at your choices here, they're looking at surface area and concentration. Well, let's talk quickly about the other ones if you were to get this kind of question. What about temperature? Okay, what about temperature? Well, temperature is the average kinetic energy. Kinetic energy is motion. So if you increase the temperature, you're increasing the kinetic energy. So if these guys are going faster, they're going to collide more often. So higher temperatures always lead to faster reaction rates. I know we're talking about surface and concentration, but let's talk about the other things that can increase the reaction rates. Now, if the reactants are gases, they're not, but if they're gases, if you increase the pressure, okay, you're going to essentially push them closer together. If I have gases that can react and I've got an external pressure, let's say they're in a balloon and that pressure is pushing them closer together, they're going to collide more often. So we've got pressure, temperature, okay, and also a catalyst, if you remember, finds an alternative pathway in the reaction, so it lowers this activation energy. So a catalyst is another, okay, another factor in helping a reaction go faster by lowering the energy barrier or lowering the activation energy. Okay, so let's go back to surface area. Well, surface area is really important because, again, if you have a block of iron in this case, only the iron atoms on the outside can collide with the hydrochloric acid or the H+. All the rest of these atoms are not exposed or cannot hit what? The hydrochloric acid. So only the outside are available for collisions. If I was to take this metal and grind it into a powder so that I have more surface area or more exposed atoms, now the HCl can collide more with the more exposed atoms. So we want to increase the surface area as much as possible. Okay, now also, another factor besides surface area that we just talked about is concentration. I'm running out of space, but I'll just put molarity as concentration. So if I was to increase the surface area, and let's make blue hydrochloric acid, increase the number of hydrochloric acid molecules, okay? Well, having more of them available is going to increase the number of collisions. So increasing the concentration will make sure that there's more of these molecules. Therefore, there's more collisions, and by statistics, there's more effective collisions. So having more of your reactants will increase the reaction rate because there'll be more of them to collide. So increasing the surface area, exposing more atoms for collisions, and increasing the concentration is the best answer here. 13 is 1. Number 14. In number 14, which process is commonly used to separate a mixture of ethanol and water? Now, a mixture, party people, is not a substance. It's made up of two or more substances. And what is a substance? It's a compound or an element. And what's so special about a substance? Well, they're homogeneous. Compounds are made up of the same type of molecules or formulas. They have the same chemical formula. Their ratio of atoms are fixed, and elements are made of the same type of atoms. So if I've got a mixture of compounds or elements, in this case, there are two compounds. What we know in a mixture, because the compounds are not bonded into something new, they are their own chemical formula, and we should be able to write this. Water, of course, is H2O. Ethanol is eth for two carbons in organic chemistry. This OL ending in table R tells me there's an OH. We fill in the rest with H's, and there's a one bond between the carbons because of the ane there. So these are two compounds, and these two compounds have two unique chemical properties. So because they have their own chemical formula, they're their own compound, they have their unique arrangement of atoms and different number of atoms on different types of atoms bonded, okay, they retain their individual properties. If they retain their individual properties, they can be separated physically. They're not bonded. So if they retain their individual properties, we can separate them by their basic individual properties. Okay, so the answer here is I have two liquids, and two liquids, okay, which are two different compounds. Guess what? We'll have two different boiling points. And if they have two different boiling points, they can be separated by their boiling points, and that's called distillation. All right, and distillation is nothing more than having some liquids, here's a container, somehow heating them to a certain temperature. One is going to boil at a different temperature, and the one that boils becomes a gas. Maybe it goes into a condensation tube where it cools into a liquid, and then we collect it, okay, in another container, and we collect that liquid. So example, to separate ethanol and water, we would basically heat, okay, our mixture, and our mixture would separate based on the differences in the boiling points. Again, this is how we separate crude oil. Crude oil, if you remember, has fossil fuels, different types: gasoline, diesel fuel, kerosene, whole bunch of other compounds that we basically heat, and we boil the liquids at different temperatures. And once we get to a certain temperature, because the mixture retains individual property, so does the individual liquid, and it'll boil differently or at a different temperature, and basically we'll boil off, okay, the water or the ethanol first. Okay, in this case we'd boil the actual alcohol off first because it has a lower boiling point, so that would boil first and then the water. Okay, in truth there'd be a little bit of a mixture there, but bottom line, distillation is separating a liquid based upon their differences in boiling points. And why do they have differences? Because they're different compounds. A mixture is not a compound. It's a bunch of what? It's two substances that are not chemically bonded, that retain their individual properties. That's really important, okay? Ionization is pulling electrons, okay? Filtration is like separating a solid from a solution. So you're making it precipitate, making a solid appear, maybe by a double replacement reaction. You can separate that solid from the solution because a solid is a crystalline structure. It's bigger, it can't fit through the pores. Titration is what we use mostly in this course in an acid base, where we use the concentration of a base or an acid using MV equals MV to solve for the other acid or base. So 14 is 1. So number 15, a sample hydrogen gas will behave most like an ideal gas under the conditions of, well, all right, well, when I think of a ideal gas, I think of the 4 requirements to be an ideal gas. And I try to always think about this in terms of the ideal student. Now, I know they're not asking for these 4 things, but if you understand what an ideal gas is, this is an easy question. So what are the 4 things? As I talked about, or I'm going to talk about, an ideal gas is like an ideal student. And what's an ideal student? Well, an ideal student, okay, is going to get to class fast, is going to get there as fast as possible, moving what? Straight lines. So they go in straight lines, they move fast. And if they collide with people because they want to get to class really fast, they kind of bounce off them to like say, not even say, I'm sorry, they just kind of bounce off because they got to get to class fast because they can't miss what I'm going to say in class. So their collisions are elastic. Okay, now to be fast, unfortunately, the smaller you are, the faster you are. So we tend to think that the volume of these gases are very, very small. So small they're negligible. But the whole idea here is that if you really think about a gas, the space they take up compared to the space they collide in is basically not significant. So their volumes are tiny. And this is the most important one, number 4. Why are they able to go fast in straight line motions? Is because they have no attractions for each other. There's no intermolecular attraction. So you can have the world's most beautiful person to the left and to the right of you, and if you're an ideal student, you have no attractions to them. You're just focused on the teacher, okay? And that's why you're able to be an independent random particle. That's important. So that's the most important of them all, no attraction. So if you think about it, if I want to make a sample of a gas behave most like an ideal gas, okay, I want them to behave in a way that they have no attractions. So how can I make a gas or gases that have probably some attractive forces go to a scenario where they have no attractive forces, where they're just totally independent particles that go in straight line motion? Well, what am I going to do with temperature? Well, let's think about this. If I increase the temperature, I make them go faster because temperature is the average kinetic energy. And if I make them go faster, they'll have less time to attract each other. So I want them to go faster. Now, I want them to be farther away as possible so they don't attract each other. We're trying to become like an ideal gas. An ideal student has no attractions for the other students around them because they're so focused on the teacher. So what am I going to do with pressure? Well, if I increase the pressure, wouldn't I push them closer together? If I increase the external pressure, I'd be putting a force on these gas molecules to be closer, and they would attract more. So I don't want that. I want them to be independent particles with no attractive forces. So what we do with pressure is we're going to decrease the pressure on this gas so that they're going to be farther away. And if they're farther away, they attract each other less. So increasing the temperature makes them go faster, so there's less time to attract. And by decreasing the external pressure, they'll be farther away and have less chances to attract. So increasing the temperature, okay, so high temperature and low pressure would make them have the least amount of attractive forces, which means they can move in straight line and move randomly, okay? And that's the best answer. Okay, there's other ways to answer that. Some people teach the polite method, but I like this understanding that we're going from a real condition. Real gases really attract each other. And remember, there is no gas that is an ideal gas, just like there's no real what? Ideal student, okay? It's only almost an ideal scenario that we wish our students were, okay, or wish the gases were. So to make a gas, which are all really have some attraction, have less attractions, we're going to give them more temperature to move faster away from each other, have less time to attract, and we're going to decrease the pressure so that they're going to be farther away from each other, and again, less ability to attract and have less attraction. So the best choice is choice 2. Number 15 is 2. Number 16. Number 16, the collision theory. This is the idea that in order for a reaction to occur, molecules have to physically collide. But when they collide, in order for a reaction to go, they must collide effectively. All right, now what's an effective collision? Well, they have to have a high enough kinetic energy to overcome their repulsive forces. Why would they have repulsive forces? Because they all have electrons on the outside of their molecules. So these electrons would repel each other. So we need enough kinetic energy in order to overcome these repulsive forces due to the electrons on the outside of atoms. And why? Because in a chemical reaction, we have this barrier. And to overcome this barrier, we need something called activation energy. So high enough kinetic energy to overcome these repulsive forces is this activation energy. So we have to have, or most likely to occur, so that a collision theory states that a reaction that is most likely to occur when the reactants collide with proper energy. It's really kinetic energy. That's to overcome the repulsive forces, and that's the activation energy. And they need the proper orientation. Remember, to be an effective collision, to be a collision that results in a chemical reaction, okay, you have to have two things: high enough kinetic energy, and two, proper orientation. Why proper orientation? Well, when big molecules, especially enzymes, especially big macromolecules, okay, with big for instance, let's take an example of a reaction that we're talking about, something we've done in organic chemistry. Let's talk about the addition reaction. Okay, if you look at the addition reaction, and if you remember this, we're going to add everything on. Let's look at Cl attacking ethene. F for two carbons, ene for the double bond in between. That's from table Q. Eth is from table P. Oops, put my H's here. And for this reaction to occur, the chlorine has to collide with enough kinetic energy to overcome the electron or repulsive force here. Okay, high enough kinetic energy, or enough energy to what? Equal the activation energy so that the reaction can go down the slide and go. But they have to collide on this double bond. If they don't collide on the double bond, it doesn't occur. So the collision has to collide with the proper orientation, has to hit the right spot and have high enough energy, and that's what an effective collision. They didn't say it in the problem, but essentially they're about what is an effective collision. And this could have been a part two, and as you go through the multiple choice, understand the part two, okay, is the same concepts as the part one. All right, so number 16 is choice 4. Number 17. In number 17, at STP, which sample contains the same number of molecules as 3 liters of H2? I call this the same problem. Okay, now STP is telling me that both gases are under the same temperature. They're both in the same temperature and pressure values. And if you have gases under the same temperature and pressure, you can compare their volumes. This is Avogadro's hypothesis. And what Avogadro's hypothesis stated, or what Avogadro's hypothesis is that if you have two containers that have the same volume, and let's just pick a volume, 22.4 liters. We don't have to pick this volume, but I'm going to. And I have two gases that are occupying exactly 22.4 liters. Okay, so they're both 22.4 liters. Terrible boxes there, but hey, I'm tall. And I have helium gas here, and I have N2 gas here, and they're both under the standard temperature and pressure. Well, we learned that this equals 1 mole. Well, so does this. And what is a mole? A mole is a word that describes a number. These have the same number of particles, and the word we use for particles is molecules. Now, helium is monoatomic molecule because it doesn't bond with anything. We'd actually call that an element in this course, but hey, okay. Nitrogen is is basically a molecule of N2, but we'll just say particles or molecules. The bottom line is molecules are particles. And if you have the same volume under the same conditions of temperature and pressure, you have the same number of particles. A mole represents that. So no matter what gas I put in this box, if it occupies 22.4 liter, it occupies the same number of molecules. Now I don't have to use 22.5 liters. I could have a 3 liter box. If I have a 3 liter box of two different gases, as long as the gases are under the same conditions of temperature and pressure, they will have the same number of molecules. So back to the question, which sample contains the same number of molecules? Well, it's going to be the one that has the same volume, same temperature and pressure, same number of molecules. And why does that work is because individual gas molecules, okay, at a particular what? Speed, okay, will bounce off each other and push each other. And if there's not enough room for them, they'll escape. The ones that can stay can exist in this area because they have the right pressure on them and the right temperature. So filling a container at a particular temperature and pressure talks about exactly the space that we need that the gases occupy for a particular number of particles. And it doesn't matter if the particle is big or small. That's what's really cool about Avogadro's hypothesis, okay? It's independent of the size of the particles. So think of same what? Volume equals the same number of particles or molecules. Let's use that word. Okay, and so 3 liters is a very common question. Sometimes you see the question with diagrams. Same volume, same number of molecules, very typical Regents question. Number 17 is 3. Number 18, the addition of a catalyst to a chemical reaction provides an alternative pathway. Okay, so look at our potential energy diagram, and let's just pick an endothermic reaction where the products have higher potential energy. These are the products and these are the reactants, and here's the pathway. And if we add a catalyst, we should know that it makes another pathway. It does not change where we start and where we finish. Okay, even though it's not part of the problem, you should know that this change of potential energy from the reactants, there should be an R here, to the products is our change in heat or change in enthalpy. And of course, in this case, it's going up, right? So it's positive for endothermic reactions. But back to the question, there's always good information about what's behind the scenes in every question. The addition of a catalyst to a chemical reaction lowers this hump. Okay, in the blue, hopefully you're not, this represents the activation energy of the forward. In the red, that activation energy of the forward reaction has been lowered because we've changed the pathway, and the reaction occurs faster. For the same amount of energy, more reactions can occur. So a chemical reaction provides an alternative pathway that decreases the activation energy. This is a big, okay, topic that continues to show its head over and over in part one, in the multiple choice, and in the free response. I call that anyway. So 18 is 4. Number 19. Number 19, a sample of water is boiling. Phase change from a liquid going to a gas. Gas has tremendous energy, tremendous potential energy, as heat is added at a constant rate. So, which statement describes the potential energy, average kinetic energy of the water molecules of the sample? So this question is really tapping into the concept of a heating curve. Now, a heating curve is this graph that you've seen. We say that energy or heat, we'll just say heat, is being added at a constant rate. That means we're not increasing or decreasing heat, is constantly being added. Okay, and what we're going to measure here is kinetic energy when we usually measure this if you did a lab like this. And it looks something like this. We have a solid becoming a liquid right here, and then it has a phase change, and then right here it's all of what? It just became a liquid. The liquid goes up until it hits a certain temperature, and that temperature would be the phase change, the point where it starts to boil. And then at this point it becomes a gas, and then we're at the gas phase. So if we remember our phases, this is the gas phase, the liquid phase, and the solid, or I like to say solid, liquid, gas, tremendous energy. Okay, so sample water is boiling as heat is added at a constant rate. So boiling is screaming we're at this phase change. And as I said, the temperature at which this happened is the boiling point or the condensation point. I know I'm trying to draw a straight line here, but if it's water at 1 atmosphere, it's going to be 100 degrees Celsius. All right, so now that we're at this phase change of a liquid going to a gas, and you know there's another phase change, by the way. There's a solid going to a liquid here, and that temperature is the what? Is the freezing or melting point, and for water, that'd be 0 degrees Celsius. Again, if we're at 1 atmosphere of pressure, these things can change, but essentially these are the numbers you use. But bottom line, also a Celsius thermometer, this is a question that pops up too in the same area. A Celsius thermometer is based on 2 fixed points. Why are these points fixed? They're fixed because the temperature doesn't change at a phase change. So a Celsius thermometer is based upon the freezing or melting point. Freezing is going this way, melting is going this way, but it happens at the same temperature. So a Celsius thermometer is based upon two fixed points, the freezing and melting point of water and the boiling point if I go this way, or condensation if I go that way. It's the same temperature. Any case, all right, so what's happening? So which statement describes the potential energy and the kinetic? Let's start with kinetic energy, because normally these graphs are based on kinetic. In fact, they always are. And I can't say enough, average kinetic energy is equal to temperature. Okay, and so temperature is your average kinetic energy. And temperature stays constant at the phase change. So at this phase change or this phase change or any phase change, the kinetic energy remains the same. Okay, so it's either going to be choice 2 or choice 1 or 3. 2 and 4 I get rid of because they're saying there's a change. Now what about potential? This one always gets people. If I'm going to add energy at a constant rate, isn't the potential energy going to increase in every segment? Don't forget that a thermometer measures kinetic energy. It doesn't measure potential. So I always tell my students, what's happening to the general flow? What's the general direction of this graph? Isn't it generally going up? Yes. And it's going up in energy because we're adding heat. We're giving it more energy, so it's going up. So if you give heat to something, you give energy to something, its potential energy increases. If I give my kids candy at night, the potential for them to act out increases. So no problem there. So potential energy increases. So even though this is leveling out, we say the potential energy is increasing only because we're adding energy. So that's why choice 3 is the best answer. Now if I go in the reverse, energy is going down. If it's going down, it's because we're releasing energy. And if you're losing energy, your potential to do something decreases. So always follow the flow of the graph. The graph is generally going down, then potential energy, if the graph is generally going up in this case, potential energy is increasing in that direction. If the potential energy, if the graph is generally going down in the reverse, if you look at it that way, the potential energy is decreasing at every segment. So because we're adding heat and we're generally going up in energy as we add heat, the potential energy increases in every segment. So choice 3 is the answer. Okay, and again, it confuses people because you're like, well, wait a minute, this line is staying constant. That constant line is kinetic energy. Right? That's what the thermometer measures. The actual potential is going up. In fact, as we go through this question even more, they love to ask in part 2, what's happening here? Kinetic energy staying constant, potential is going up. If we're adding heat, if we're going the opposite way, kinetic energy is staying constant and potential energy is dropping. Okay, because you're losing energy, losing heat, losing your potential to do some extra energy. Okay, very important. They love to ask about what's happening at a phase change. And by the way, they could say, well, why is the temperature staying constant? Why is the kinetic energy staying constant at boiling as I'm adding heat going this way? And you would say that the kinetic energy is being converted to potential energy. That's the catchphrase. Now, there's another way you can say that. You could say that the molecules are being pulled apart, okay, at this physical change. Okay, so number 19 is 3. So number 20 is a straight definition question. Entropy is a measure of the disorder of a system. Okay, so it sounds something like enthalpy. You may have learned this in your chemistry class. Enthalpy is the delta H, the change of overall heat in a reaction. The entropy, though, is the disorder, and we should know that the disorder of a system is increasing for spontaneous reactions, but more importantly, the amount of disorder, for instance, a liquid going to a gas, you're increasing your entropy, your delta S, okay, although they don't use it that way. And you're also, if you have one particle breaking up into 2, like a decomposition reaction, the entropy is also increasing. So different ways to observe that. And basically the way of the universe is that things in nature have a pathway for reactions to go if the entropy is increasing. So something you'll hear about, but it's the measure of the disorder of a system, the dispersion of energy big things breaking apart into smaller pieces, or a solid which is more organized than a liquid, and a liquid is more organized than a gas. And as you go from a solid to liquid to a gas, the amount of disorder increases. And again, decomposition reactions, okay, are showing that as well. So 20 is choice 2. Number 21. Okay, looking at 21, and we'll just circle that. Number 21, okay, you look at which element has atoms that can bond with each other to form rings, chains, or network structures, and that's going to be carbon. Okay, you should know that glucose or amino acids, any organic compounds, okay, are carbon based, and there's all different types of ring structures that we use in chemistry that have carbons in them. This is an example of a sugar, okay, that we either use for, let's say, in DNA, deoxyribonucleic acid, or just, simple sugars like glucose, okay, can be formed in rings. Okay, normally aluminum or metals don't make ring structures. They don't make network structures either. What's a network structure? Well, if you have carbon that's in a tetrahedral shape that keeps going in all directions, that's diamond. Okay, you can also have a graphite, but these elements, okay, do not form rings or chains. They're screaming to you. These are all elements. Argon doesn't bond with anything. Calcium's a metal. It makes metallic bonds with itself. Same thing with aluminum. So carbon is the one that makes or covalent compounds. A network structure is a covalently bonded compound. But that's not something you have to know anymore. So that really wasn't about it. But knowing that rings and chains and long hydrocarbons are carbon-based, but more important, living organic molecules are carbon-based, and a lot of them have long polymers that have carbon in them, like starch, which is glucose, and glucose is a sugar that's carbon chained. Okay, and of course, we're an organism that needs to eat sugar for energy. So we also build things with the energy we get from food, like proteins, and proteins, okay, are mostly carbon based with a nitrogen attached to it. Okay, and so polypeptides have many carbons in them. So it's all about the carbon when it comes to rings and chains. This is a question I see popping up all the time. All right, so 21 should be clearly 3. 22, what's the number of electrons shared in a multiple carbon-carbon bond in a molecule of one pentyne? Now, this is an organic question, and in fact, so is 21. And what's interesting sometimes in these tests is that these questions go kind of in order. So knowing that you're in an organic area, now how do I know I'm in an organic area? Well, this was about carbon. Hopefully you could see that. And now we're talking about carbon-based naming system, the IUPAC naming system that's based on the carbon structure. So they're telling it how many electrons are shared. And remember, you understand carbon-carbon bonds are sharing bonds because these are non-metals. They're above the staircase. So the question is, how many bonds exist between the carbons in one pentyne? So we know we have 3 reference tables that help us with organic chemistry questions. So let's go there. I'm looking specifically for ine. Okay, now pent tells me how many carbons there are, and we know there are 5 from table P. Ine, where do we look for that? So let's go to our reference tables to see that where and what it tells us. So table Q is our friend, and like I just said, table P is our friend too for the prefix in that name. Notice it was pent. We don't need it for the problem, but that gives me 5 carbons. Now if you notice, it was an ine ending. Okay, so an ine ending tells me something about the bonds between the carbons. So the pentyne, the pent tells me how many carbons, and there are 5. And again, that was important for that question, but you may need it for something else. But the YNE ending is telling me that there is a triple bond. And if there is more than one double bond, we call these guys unsaturated. And they're unsaturated because they have what? Under the amount of H's that are possible, because carbon makes 4 bonds. So in this case, because it was ine and table Q tells us an ine ending is a triple bond, okay, we know something about the bonds between the carbons. And what are those bonds? Well, they're triples. So we have essentially in the multiple carbon-carbon bond, we know by the ine that we have a triple bond. Now we have 3 other carbons, but we don't care. There's just there's a triple bond in the first carbon. That's what the 1-pentyne tells me. It doesn't matter there. But what do we know? He's a triple bond. Now, something we should know that a covalent bond, party people, is a pair of electrons. Carbon has what? 4 bonds it makes because it has 4 valence electrons. All right, so even though we don't need this electron here, I was showing you how this would bond to an H. H has 1 electron. Another carbon would have a bond, and it would bond 4 places. The bottom line is carbon makes 4 bonds. This would be 1 bond here. This would be the other bond. But between the carbons, because there's 3 bonds, because of the what? The ine that we get from table Q, we know that there's 3 bonds. And how many are shared? Well, there are how many number of electrons? 2, 4, 6. 6 is the answer. Now, careful. Sometimes in these questions, they ask for how many pairs. This question did not. If they wanted pairs, that'd be 3. A pair is a bond, but they look for the total number of electrons shared in the multiple carbon-carbon bond, and they said multiple because they didn't want to give it away that it was a double or a triple. We don't talk about these because these are single bonds. So in this scenario here, there's a total of 6 electrons, and that's why 22 is choice 1. 23. Number 23 is another example of an organic question. And I can't say enough that a lot of times these questions are bundled together. Knowing it's an organic question, okay, 21 through 23 are all organic questions. So knowing that sometimes you're in a cluster can help you. Now, butanol, butanone, and diethyl ether. Notice these are compounds that we should be able to recognize based upon table R. Okay, so butanol, butanone, and diethyl ether. Okay, what's so different about them? Well, let's see if we can just write their formulas. Okay, and understand that. So table R is our friend. Let's go there. So we had butanal, butanone, and they probably gave me a number for that. And no, they didn't. Just said butanone, and then it said diethyl ether. So diethyl ether. So these are the compounds. Now, how to know butanal was an aldehyde? I see the al ending. I see the al ending. Okay. Now, what do I know about this? Oh, here's an ether. That's an ether, right? There's an ending. And the one is an one here. So these are the 3 different. Now, but, these are what? Let's just do the butanol real fast. We should be able to do this. Write this. This could be a part 2 question. So just because they're not asking you to do this, really helpful to understand the behind the scenes skills in each question. So let's just write this. They could say, write the Lewis dot diagram or the structural formula of butanal in your part 2 section. So let's do that. So butanal would be 4 carbons. Now, how do I know it's 4? Because it's a but. And if you go to table P, okay, and I'm going to try to go to table P without making this crash. Okay, table P says a but, okay, is a 4 carbon. So let's go back to our table R. So 4 carbon. Ane, we take the E away. I'm sorry, ane, we're in butanal. We're doing butanal now. So butanal, okay, would have the ane, so single bonds between the carbon, and the al means we have this functional group where we have a carbon, the last carbon is double bonded to an O, single bonded to an H, and this R means the rest of the compounds. This is the rest of the compound. I don't need that, so let's get rid of that, and let's add the H's in, and that's butanone. Okay, so I'm sorry, that's butanal, all right, and let's do butanone. Okay, and I guess I'm making this more complicated, so I'll write it next to it here. Okay, so butanone is a ketone, and I'll write it right here for this one, so you're not going crazy looking all over the place. Okay, and we'll do that. And so butanone is 4 carbons too, and it's single bond to the ane. And somewhere in the middle, notice this is the R, this is the rest of the compound, we have a double bonded O. Okay, somewhere in the middle, this is the rest of an organic compound, the rest of the other. You have a double bonded O. fill in the rest with H's so that every carbon has 4 bonds. Notice there's none here because carbon has 1, 2, 3, 4. And then we'll do diethyl ether. And let's just get rid of this. Again, Mr. Grodsky, I have to do all of this. Well, sometimes you do, and you have the time to do this. Okay. And again, as you do more tests, you can recognize these questions faster. So diethyl ether, well, that means we have an O in the middle. Let's draw it. And then, wait a minute, diethyl. This is a methyl ethyl ether. Here's the example. There's a meth group, which is from table P, and an eth group. It's a 2-carbon compound from table P, but I have a 2-ethyl group on each side. So I'm going to have a CH2, CH2, and a CH3. If I don't like any of that, there's an O bonded to a C, and it's a 2-carbon group on each side. And then I fill in the rest with H's so that every carbon has 4 bonds. So you can see where I get the CH2 there. Okay. Bottom line is, there's that compound. Okay. And so what do I know? Well, I do know, if I count, I have 1, 2, 3, 4 carbons. 4 carbons. I have 1 oxygen. Okay, and how many H's? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 H's. And I have an O for this diethyl ether. How about butanol? I know I drew it down here. 1, 2, 3, 4 carbons. So my butanol is 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8 H's. All right, 1, 2, 3, 4, 5, 6, 7, 8 H's. And there's 1 O. Why not? And then we have butanone. 1, 2, 3, 4, 5, 6, 7, 8 H's. 4 carbons, 1 oxygen. Okay. And so what we can see right away is they do not have the same chemical formulas. These two, butanol and butanone, are actually isomers because they have the same chemical formula but different structure. Diethyl ether, okay, does not have the same chemical formula. So these two are isomers, the butanol and butanone. But what we know, the reason they are called different chemical compounds is because of the different arrangement of atoms. As I'll say in different parts of this class, structure is king. So these have essentially different properties because of the different types of arrangement or structures their functional groups give them. So it's back to the question. So diethyl ether, propanol, and butanol have different properties because they have different structures, and they differ in the number of types of functional groups. Okay, choice 3. They do differ in the number of hydrogens, but they don't ask that. So they do not differ in the carbons. They all have the same number of carbons. They all have the same number of oxygens. In terms of radioactive isotopes, that's a poor distractor, poor choice. You'd have to know something about the individual atoms and the nucleus of atoms. That's not a nuclear question. This is an organic question, so this makes no sense here. Although there is an isotope of carbon, carbon 14, that we use for carbon dating because it's a beta emitter, or undergoes beta decay, become nitrogen. That's not what this is about, so stay away from question 4. 23 is choice 3. Number 24. What occurs when a magnesium atom? Whoa, I hear the word atom, or you hear the word atom. Okay, you must think neutral particle. Now, I always say, I say atom, you say neutral. Atom, you say neutral. Say it. Neutral, atom, neutral, atom. Good job. Now, not a dance party, but what helps you remember is anytime you hear atom, you think neutral. Now, of course, neutral means it's 0 charged. Now, why would an atom be 0 charged? Because there are positive particles called protons, and there are also what? Negative particles called electrons. And these guys must be equal to each other. Okay, therefore, the entire particle is equal to 0. So the protons equal electrons. Very, very important concept, especially if they were to ask you, hey, what is or what are the number of electrons that are left when a magnesium atom, hey, neutral, becomes an ion? Now, what is an ion? An ion, of course, is a charged atom where it is not neutral. Now, in the case of magnesium, if we go to the periodic table, this is going with the atom, and this will be an ion. To know what charge the atom likes to become, let's go to the periodic table. And magically, here it is. And here's our magnesium, upper right-hand corner. This is the charge that magnesium likes to become when it becomes an atom. All elements listed on the periodic table are atoms, which means if they were to ask you how many electrons does a magnesium atom have, well, it must be that the protons, of course, equal the electrons. And so this bottom number, of course, is the atomic number, and all elements are based upon the number of protons, or they differ by their proton number. So they must have 12 protons, well, therefore they must have 12 electrons. However, this question is about the ion. So magnesium becomes +2. Because magnesium atom becomes the magnesium ion and only has one choice, +2, just like all of its family members in the same what group. This is the alkaline earth members. They all become +2 because all metals become positive. You can see that all of these listed elements here are all metals. They love to lose electrons. And if you were to write a half reaction, which you don't, you can see that 2 electrons are lost. Okay, so we know that magnesium atom becomes an ion. That is +2. Okay, so now, of course, what occurs when this happens? Well, you just saw me write a half reaction to become +2 because it's still magnesium, okay? And because it lost 2 electrons, and it has to lose 2 electrons, as we saw in the periodic table, it's got a mass of 24. I'm rounding that off to the most common isotope. And this, of course, is atomic number 12. So the number of protons are 12. And so then the protons in the magnesium are still 12. We didn't lose 2 protons. If we did, we'd change the symbol, right? Atomic number of protons, is unique for each individual atom. Okay, so because it's still magnesium, there's still protons are the same. So how can we become +2? Can't gain 2 protons. It would no longer be magnesium. It must have lost 2 electrons. And all metals lose electrons. All metals become positive because they hold on to electrons loosely. So for it to become this ion, and they didn't say this, so you had to either know that or look at the periodic table like we did, electrons, okay, are definitely going to be lost anytime we have an atom, neutral, hey, you got to say it, becomes an ion that's positively charged. Metals lose electrons because their electrons are loosely held. You can't find me a metal in the periodic table who becomes negatively charged. They all become positive. Now, what happens to the oxidation number? Well, losing electrons, or electrons are lost, is oxidation. Remember Leo the lion? Hey, Leo the lion. So losing electrons is oxidation. So you have to lose electrons, so it's oxidation. And therefore, in oxidation, or in the case we have a regular atom, what's the charge of an atom? Neutral. So you're going from 0 to what? To +2. Your charge is increasing. So this was really a question about, do you understand that magnesium becomes positive ion because it's a metal, like all metals? You could look that up. And that when a atom that's 0, like metals, become positive, they are oxidizing. And therefore, their oxidation number is increasing because they're losing electrons. So any case, number 24 is 3. Number 25. In number 25, energy is required to produce a chemical change. During what? Well, first and foremost, boiling and melting are not chemical changes. These are phase changes. H2O liquid goes to what? H2O gas. Notice the chemical formula is staying the same. Same thing with melting. You're going to go from a solid to a liquid. The chemical formulas stay constant. Okay? Now, Chromatography is a technique that we separate a mixture based upon its individual properties and solubility. Mixtures are not bonded. They're basically put in close proximity. They're made physically, they're separated physically. So chromatography is a separation technique that's a physical separation technique. So that can't be the answer. And of course, the answer here is electrolysis. And remember, electrolysis is where we have a battery or a voltaic cell that helps us drive a reaction. Let's say I want to plate the chicken fork, okay? And I want to plate it with, let's say, gold, AU. So I'm keeping it here. Notice there's no salt bridge. And basically what I'm going to do here is connect it. If this is the negative part of the battery, it's the anode. It's going to make this the negative cathode, right? Anode to cathode, right? So electrons flow this way. Electrons build up. We're going to connect the gold to the positive part of the battery, which makes this positive. And if this is the anode, this must be the cathode of the battery. And electrons, if this is the cathode electrolytic cell, this must be the anode. Electrons flow always from the anode to the cathode. Now you don't need this diagram, but the anode is oxidation. Solid metal becomes an ion here, so we make Au plus 3. So oxidation occurs. Au, solid metal, becomes Au plus 3. Its charge goes up, and you give off 3 electrons that go back to the battery. This Au plus 3 hooks up with the electrons that are being pumped from the anode. Okay, and the Au plus 3 gains the 3 electrons. It becomes Au0, which is the solid, and of course plating occurs there. But if I was to cut these leads and not have the battery force this action, this would not occur. It would just sit there. And this is a non-spontaneous process. It requires energy. The battery is the energy. Think of electrolysis. Electrolytic cell is endothermic. It needs energy. It's never going to work. When you plug in your phone doesn't charge by itself. You need to put energy into it. All right, so carrying the pony up the hill. All right, so choice 2 is the answer. I know I overtaught it, but I'm trying to teach you everything you need to know about these questions. Number 25 is 2. Moving on. Number 26, an arrhenius acid with an arrhenius base. This reaction produces water in it and what? Well, people, I don't understand. They get all crazy when they see arrhenius. Oh my gosh, I don't know this person. Okay, it's not a history test. Arrhenius was the person that first defined an acid and first defined a base. And they had the easiest definition because it was the what? The first definition. To be an arrhenius acid, you have to have an H in your compound that's given off, because acids do what? They dissociate into H plus, and let's say what's remaining, we call this a conjugate base. But if you add H pluses to the solution, you're an arrhenius acid. So because it has an H in front, HCl is an arrhenius acid. To be an arrhenius base, you have to have a compound that when it breaks apart and adds OH minus to the solution because it has it as an ion. So that's pretty simple. So if I give you an example of an arrhenius acid that has an H to give off as an H plus, and an arrhenius base that has a hydroxide ion, an OH, by the way, listed in table E, okay? And what we have here is we're going to have, obviously, the H is H plus, this is Cl negative, Na is plus, and OH minus is negative. So the H plus is going to hook up with the OH minus. It's like a double replacement. So we're going to make HOH, which is basically water, and you could write it that way. And what else are we going to make? Well, the Na plus and this NaCl, hey, that's a ionic compound. Another word for an ionic compound is a salt. And so the type of reaction that exists between an acid, whether you want to call it arrhenius or not, or a base, is a salt and water. Essentially, this reaction is a neutralization reaction. But it's also a double replacement reaction where the ions just kind of switch partners. You can think of it as a type of double replacement reaction. Okay, so acid base makes salt in water. I did a demonstration years ago in class where I took a strong acid like HCl and added it to a strong base, and I had equal amounts of acid and base, and what I was drinking when I poured them together was salt water. Okay, so it's a salt, and 26 is choice 1. I have seen questions where they ask you to finish, okay, in part 2 what the two compounds are if you have this acid and base. So again, as I go over these multiple choice questions, I'm going deep into them because the concept behind them could be in a part 2. So number 26 is choice 1, and number 27 coming up. So number 27, one acid base theory. Okay, I don't know why they talk about Arrhenius. So if you notice in number 26, and we just did it if you were with me, 26 was an acid base question. Notice number 27, also an acid base question. So we're in the acid base kind of cluster of questions that seem to kind of go together. But we already talked about Arrhenius in question 26, and that just means that you to be an Arrhenius acid, you give off H plus ions in solution, and to be an Arrhenius base, you give off hydroxide ions. Now, there's another theory. They call it Bronston-Lowry, but the New York State curriculum doesn't call it by name. They call it the other theory. So the other theory that is more encompassing and better than Arrhenius theory, because I don't want to give you too many, I guess, people, is the Bronston-Lowry theory, but it's the one where we treat the acid and base as either a proton donor if you're an acid or a proton acceptor if you're a base. Case in point, if I have HCl again, and I have ammonia and H3, okay, what can happen is the proton, the H plus from the acid, is donated to the NH3. So in Arrhenius, we say HCl is an acid because it produces H plus ions. But in truth, it's an acid because it gets donated to a base. And a base doesn't have to have a hydroxide. A base is just a proton acceptor. H pluses are being accepted here. So this guy is going to hold on to an extra H plus. So it is NH4 plus 1. And of course, because HCl was given off, what remains is Cl negative. Okay, so they love to give these equations sometimes. They're called weak acid base equilibria. And they'll say, hey, what is NH3? Well, look at NH3. And in the future, because we talk like that in the future, there's one more H, so this must have accepted an H and an H plus acceptor. Okay, it's all about the H plus, so choice 1 and 2 is gone. So a one acid base theory, which they really mean their other theory that they don't want you to name, which is the Bronston-Lowry theory, which is about the donating of the H plus. So an acid is an H plus donor. Okay, remember Arrhenius just says H pluses go in solution, but the more encompassing, better definition, the Bronston-Lowry, which they're going to just say the other theory, in this case they say 1, okay, is an H plus donor. If you knew any of that, H pluses are given off by acids, so it's better to be a donor. Okay, it's not about H negatives. So number 27 is that an acid is an H plus donor, choice 4. Okay, number 28. So number 28. Which phrase describes the decay modes and the half-lives of K37, K42? First and foremost, this number is the mass number. And why are they giving a mass number with an element symbol? Because they're describing the type of isotope of potassium. All atoms have different isotopes, different forms of the same element. What makes potassium potassium? Atomic number 19. It likes to have 19 protons, but it can have different number of neutrons. Remember, protons and neutrons have about the same mass. So the mass number is the protons and neutrons. So K42 has what? 5 more neutrons than K37. And that number differences of neutrons can make the atom be unstable. Hey, we're in a nuclear chemistry area of this test. Number 28, 29 and 30, if you look carefully, all have something to do with nuclear chemistry, and understanding that questions cluster together could be something that helps you. So where do I look to see which phrase describes the right decay modes? The decay modes mean what kind of particles do they like to emit these nuclei of these chemicals to get more stable if they're radioactive? Do they have the same decay mode, which mean the same particles? Okay, do they have the same half-lives? So we go to a place that tells us that, and that is table N. So let's go there. And here we are with table N magically appearing for us. And we're going to scroll down and focus. Again, this is selected radioisotopes. These are some selected, not all of them, but some radioactive elements because their nucleus is unstable. And this is telling us what kind of particle they like to emit. So let's go find our K37 and K42. And there they are. And so K37 undergoes a B positive decay mode. And you may say, well, okay, and what's that? Well, we'll get to that in a second. K42 gives off a B negative, so clearly they're different. And this number here is the half-lives. If you remember, half-lives is the amount of time it takes for half of the substance to decay or transmutate into another compound. So B positive, clearly we can see, clearly the half-lives are different, and clearly the decay modes are different. But what are these decay modes? Well, B positive and B negative. If you go to table O, this tells you it's a positron, and in table O, this is a beta particle. So the decay modes are different and the half-lives are different. Let's go back to the problem. So in 28, as we just saw from table N, they have different decay modes. One's a positron, one's a beta emitter, and they have different half-lives. So this was directly off table N. It was measuring your understanding that you needed to look somewhere for this information. Okay? All right, so number 29. Which particle has a mass that is approximately equal to the mass of a proton? So in my opinion, number 29 could also be the first question because nuclear chemistry sometimes is taught with atomic structure. A lot of times it is. So again, who has the same mass equal to the mass of a proton? This is probably something you already know, since if I have carbon 12, that's the mass number, it's the isotope of carbon, and its atomic number is 6. If you remember, this bottom number is the proton number, identifies the atom. Carbon only has 6 protons. This top number is the mass number, and it's protons and neutrons. So if you remember, you subtract out the protons and you get neutrons. So that only works if the protons and neutrons have about the same mass. So 29 is 3. But if you did not know that, okay, could there be a place? And the answer is yes. Table O is the place you want to look. Table O. Okay. I guess if you're from Brooklyn, depending on what part of the country, or actually New York, it's a New York test, right? So table O is a place to look at how particles differ. Let's go there. So table O, and here we go with a proton. Top number is still the mass number. Bottom number is the proton number or the charge number. It really helps to see it that way. So it's +1. And a neutron, there we go, has a mass of 1. And so does a proton. So they have the same mass. Notice the electron. I don't see it. Well, electron is really the beta particle, right? In the old reference table, they used to have this here. Electron has 0 mass when you consider how small it is compared to a neutron. In fact, it doesn't have a 0 mass. It actually has a mass that is 2,000 times smaller than that of a neutron and proton. And it has a charge of -1. And you can see the alpha particle has a charge of +2. Because of 2 neutrons, you have a total of 4. Any case, gamma radiation has no mass and no charge, and that's why gamma radiation is the most dangerous, the most penetrating. It has no mass. It's basically electromagnetic radiation, okay, and no charge, meaning it doesn't deflect away from something. Okay, so there we go. So number 29 is 3. You probably would need table O, but hey, it's there for how you compare other particles. Okay, number 30. Number 30. Which change occurs during a nuclear fission reaction? Now, look where we are in the test. It seems that when we go from 1 to 30 in the test, and this, of course, is the Part A section, okay, we go through the entire, all the units of the test here. So we go from atomic structure from one all the way to nuclear chemistry. Now, your teacher might have taught the course in a different manner, but when you get to 29, 30, you get these cluster questions that are nuclear chemistry. In fact, if you can see, 28, okay, was our first nuclear question about decay modes. Table N helped us out there. Type of particles that the selected radioisotopes gave off. 29 was talking about the individual particles that are given off that make those individual decay modes. Okay, now of course there's no decay mode for neutrons, but table O, as we learned, shows us all those different types of particles and how they differ. And 30 is another nuclear chemistry question. So knowing where you are in the test can help you. And one thing about nuclear reactions, okay, is that they have nothing to do with electrons. Everything that we've done in the entire course is about electrons, except for nuclear chemistry or nuclear physics. Really, it's what it is. So the one thing they love to play on you to make sure you understand that this has nothing to do with chemical reactions. So do not think that this is a chemical reaction. It's a nuclear reaction, and that's why nuclear reactions, although not written in 28, 29, or 30, for instance, carbon-14, you'll see an element with its atomic mass number that's basically individual for its isotope, okay, like carbon-14, and then maybe it giving off a beta particle, right? This is given us in table O, and then we can figure out that, well, what number plus -1 is 6, here's a 7, and what number plus 0 is equal to 14, and atomic number 7 is nitrogen. And we can do these nuclear equations because it's about the nucleus changing, how many protons and neutrons, how they're changing. In this case, when they naturally, because there's just one thing, transmutate. So it's really important that you understand that. I'm trying to stress that because we want to get rid of the type of questions that are chemical reactions. So let's look at them. So which nuclear fission? Okay, so covalent bonds are converted to ionic bonds. Well, these are something that doesn't happen. And number two, covalent bonds and ionic bonds are about electrons being shared or transferred. So this is a what? This is a chemical reaction. Get rid of it. They're going to give you those choices. All right. And then isotopes are converted to isomers. Nowhere in your course how that ever happened. Okay, an isotope like carbon-14 is a particular type of carbon. For instance, the most common isotope is carbon-12. Why is it 12? Because, well, because to be carbon you have to have 6 protons. So if the mass number is 12, you have 2 less neutrons. So isotopes, what the heck is an isomer? An isomer is a structural formula. Like if we look at ethane, eth for 2 carbons, ane in table Q is a single bond because carbon makes 4 bonds. This is a structural formula. We could write it CH3, CH3. It shows how they actually make the structure in the bonds. These isotopes, which is a particular type of atom with a unique number of neutrons, have nothing to do with the structural formula of atoms bonded to each other chemically. So 2 you get rid of. Okay, and of course temperature converted to mass. That's an interesting one. Kinetic energy converted to mass. That's just flat out wrong, makes no sense. So the winner here is matter is converted to energy, and this is important even though it's the only choice that makes any sense. Really important one. Your teacher may have written E equals mc change in T. This is Einstein's equation, and it helps you understand that energy and matter are interconvertible. However, we don't know how quite to do that. But in nuclear reactions like the one I drew here, or in nuclear fission or fusion, any nuclear reaction, a little bit of mass is missing. In chemical reactions, we have conservation of energy and mass. But in nuclear reactions, and I'm going to say this again, whether it's fission, where we're splitting an atom into smaller pieces, or fusion, where we're taking smaller atoms and combining to make bigger at fusing together, or if it's just natural transmutation like this, or artificial transmutation where you have two reactants, any nuclear reaction, okay, there's going to be some mass missing. And a little bit of mass, just a little bit, times by a what? A huge number, which is the speed of light squared, is going to give you a lot of energy. So a little bit of mass is missing as energy is released in these reactions. We call usually that called mass defect. We're defecting some of that mass in these nuclear reactions. They have something to do with the binding energy that keeps the nucleus together. So the bottom line is mass, okay, is lost, and that lost mass is converted to energy. That's what this is about in all reactions. Now, as I go over this concept, you should know nuclear fission and nuclear fusion, okay, are the two big boys in our energy released type of nuclear reactions. And even though nuclear fission, making the atomic bond, gives off a tremendous amount of energy, okay, nuclear fusion gives off an order of about 1,000 times more energy. And nuclear fusion, if it's giving off more energy, therefore there's more mass missing. That's important. So both of these, all nuclear reactions, okay, have some missing matter that's converted to energy. Nuclear fusion has a lot more because it gives off a heck of a lot more energy. But chemical reactions do not have missing mass. Their mass is always conserved. 30 is 4, number 31. So here we are in part B1. Now these are the continuation of the rest of the multiple choice questions, and there's 20 of them in this test. And in any case, these are typically a little more challenging, or two-step problems. Sometimes I see that, sometimes I do not. However, what they do, just like 1 through 30 went through the entire course, this resets the course again. So we're going to start with atomic structure. Notice this is an isotope question, and then we're going to end up on usually back to nuclear chemistry like we ended up. So again, knowing that, they may help you to understand what type of question you're seeing. Okay, so number 31. Back to atomic structure like we were in the first couple of questions. It's resetting. Which notations represent hydrogen isotopes? Iso means same, and isotope, as I talked about in number 30, is the same atom, different number of neutrons, and therefore gives it a different mass. So what makes an atom similar or the same is the atomic number. So if you're going to be hydrogen, you have to have the atomic number 1. And if you look at your choices, choice 2, 3, and 4, okay, the atomic numbers are different, and that's never going to work. If they're going to have an H, and H implies the atomic number should be 1. Okay, so all of these H's should have a 1 on the bottom number. And so therefore, they're all wrong. Notice choice 1. Choice 1 both has atomic number 1, which is unique for the hydrogen atom, but their mass number is different. So H2, we would write this one as hydrogen 2, and this one is hydrogen 1. They're different forms of the same element. They're both hydrogen, and what makes them the same is the proton number, which is the atomic number, which is the bottom number, is the same. Now the top number is different, and that is different because we have different number of neutrons. Protons and neutrons have the same charge. Mass. So therefore, when you subtract them, or when you subtract the top number from the bottom, or the bottom from the top, I should say, you get the number of neutrons. So 1 minus 1 gives us 0 neutrons for this one. 2 minus 1 gives me 1 neutron. And the reason why you can do that, the top number is protons and neutrons. This bottom number I just talked about that identifies the element is the proton number. Since protons and neutrons have about the same mass in table, what is it? O, okay, when you subtract, you're going to get just the neutrons. So same atom, different number of neutrons is an isotope. It's a heavier or lighter form of the same element. Choice 1 is the answer, only answer that makes any sense, because hydrogen, for it to be hydrogen, must be atomic number 1. And if I don't know that, one place to look is my periodic table. And there it is. To be hydrogen, but you're going to have one proton, atomic number 1. The periodic table is built in order of atomic number. Okay, so lithium, to be lithium, you have to have atomic number 3. And of course, this atomic number equals the proton numbers. And don't forget that these are all written as atoms, neutral. Atoms are always neutral. So the bottom number is the proton number, but it also tells me the number of electrons if it's an atom. So hydrogen has 1 proton, right? 1 proton, which gives me a +1 charge, and it has 1 electron, which is a -1. They have opposite equal charges, okay? Because hydrogen has to be 0. These charges are the charges the atom likes to become when it becomes an atom. Notice this top number is 1.00794. It's the average of all the existing isotopes. Because there's always one isotope of every element that's in higher percentage, this rounds off always to the what? The most common isotope in nature. So this is rounds off to hydrogen 1. And that tells me 1 minus 1, the most common form of hydrogen with 1 proton, has what? 0 neutrons. Okay? All right, moving forward. Number 32, naturally occurring gallium is a mixture of isotopes that contain 60.1% of gallium-69 and 39% of gallium-71. All right. Which numerical setup can be used to determine the atomic mass of natural gallium? All right. So this is called the weighted mass problem. The reason why gallium, okay, that's a G I should say, has a number, a decimal number, just the reason why all atoms have decimal numbers in their atomic mass number is because they're basically a weighted average of all the existing isotopes that exist for that atom. What's a weighted average? Well, real quickly, to give you a sense of what this means is, if I have carbon 12 and carbon 14, these are isotopes, different number of neutrons, same atomic number, okay? And if I was to do a simple average, 12 plus 14, okay, which we should all know is what? 26, right? 14 plus 12 is 26. Divide by 2. 26 divide by 2, right? So all I'm doing is 14 plus 12, and this is 26 divided by 2 gives me 13. So you would think, based on what I just did here, that the weighted average is carbon 13, right? It's the number in between if you didn't see that. But we don't do this. This is not what a weighted average. We didn't weight these. When I do a straight average, I'm assuming what? If I have two numbers, didn't I assume that 50% all of my carbon was carbon 12 and 50% is my carbon 14? Yes, party people, and that's what happens. So if I assumed it was 50%, I could do an average another way. Let's do 50% of 12. If you don't see what I'm doing, 50%, half of 12 is 6. Then you're going to add to 50% of 14. What's half of 14? 50% of 14 is half, is 7. Then add them together. Oh, we get 13 again. So we can do averages by using percentages. Now what I just did was I did 50% of both of these, assuming they were equal percentages. Well, party people, that's not how it works in nature. Notice in one example, there's one that's 60% and one that's 30%. So we know these relative percentages, so we're going to do this for gallium. Okay, in this case, we have gallium, which is 68.93. And we have gallium that's 70.92. I put spelling C there. Gallium. Now, what we're going to do is, instead of doing 50%, we're going to do the percentages. So we're going to find 60% Remember, I found 50% of 12. Well, I'm going to find 60% of 68.93 of this one. So I'm going to find 60%. Now, when I do percentage, I move the decimal place back. So I'm going to take 0.6011, and then I'm going to times it by this number, 68.93. That's the atomic mass. Just like here, basically what I did was I took 0.5, because 50% is 0.5, and I times it by 12. That gave me this 6, and then I'm going to, what? Add it to the other one. I'm going to find 39.89, which is going to be 0.3989, right? Because I'm just going to move the decimal place over 1, 2, and then I'm going to times it by the atomic mass, which is not 14, it's 70.92. And that would be my answer. And of course, the best choice there is right here. So take the atomic, well, this is the percentage, right? This is the percentage, times it by the atomic mass, and then take this percentage, and notice it changes when I move the decimal places 2 places over, and I times it by its atomic mass, and so that's why choice 3 is the correct setup. All right, now, just so you know, I've seen choices where they used the 60.11, but then they divided this by 100 to do so. Now, you don't have to do that, but you should be able to recognize what this was. This is the classic weighted average problem. Okay, you don't even have to come up with the answer, and a lot of times in part 2 they'll just ask for the setup or the answer. And I've seen old questions, although I haven't seen this in a while, where they did this for a 2-point question for the setup. So sometimes they'll just ask for the setup and you'd be golden, and that's all they're looking for. Number 32 is choice 3. Okay, and again, just be aware sometimes they don't move the decimal place. You could actually divide by 100 there to do that. All right, so choice 3 is the answer. All right, and moving forward to number 33. Number 33, which list of symbols that represent elements represents nonmetals only? Now, my nonmetals are my smalls. We should know, going across the periodic table, the nuclear charge, its charge inside the nucleus increases. As we go down, we get bigger too, but the bottom line is, okay, as we go across and up, okay, we're looking for the upper right-hand corner of the periodic table. What's so special about nonmetals? They have a high attraction for electrons. That's the reason why, okay, that's the reason why they're so small. They basically, their nuclear charge, or their positive nucleus, okay, pulls in electrons very, very well, and are able to attract other, and we call that attraction for other people's electrons electronegativity. So they hold on to electrons tightly. In fact, they tend to gain electrons because of that and get reduced, gaining electrons, and become negatively charged. Okay, so if you don't know where this is, let's go to the periodic table. So here I'm in the periodic table, and upper right-hand corner is your smaller atoms. Notice they like to become negatively charged when they become ions. Now, the top one is usually the oxidation state that they become more. So you can see all these negative charges. All these guys here that become positive, you can't find me a metal who's bigger, who holds on to electrons more loosely. Okay, you can't find me a metal, all right, that becomes negative. The ones that can become negative are your nonmetals. And to know that, there's this staircase here that delineates or separates your metals from nonmetals. But before you do so, you should be aware that we have something that has metalloids. Now, what are metalloids? Metalloids have properties that are like nonmetals, and they have some attraction for electrons, and they're like metals in the fact that they kind of hold them loosely, so they're kind of in between. They have properties of both. So boron, silicon, arsenic, tellurium, germanium, and antimony, and if you didn't know Sp was antimony, table S gives you the name for the symbol, separates these two different types. So here are your nonmetals, and here are your metals. Notice, okay, if you look at this periodic table, there are going to be a heck of a lot more metals okay, that are to the left of that staircase than nonmetals. Also, one little important point is that hydrogen, although written way over to the left here, okay, right here, is a non-metal. It's written here because it has one valence electron, but it's kind of separated so you know that it really does not belong. I always call it the Waldo. When you look at its electronegativity, it's higher. All right, so we're going to pick some elements that are non-metals only and not our metalloids that are on the staircase, including these two. So back to our question. So now that we know where our nonmetals are, we can see that number one cannot be the answer. Boron is a metalloid. It's on that staircase. Aluminum is a metal. Okay, so is gallium. Two, lithium's way over to the left. It is, okay, a metal. We're going to get rid of that. Carbon, good. That's above the staircase. Okay. Oh, silicon's is a metalloid on the staircase. They just want metalloids. So we're left with choice 4. And phosphorus, sulfur, and chlorine are all to the right of the staircase. They're not metalloids. And these are only choices that have the nonmetals. Number 34. Number 34, in the formula XSO4. What the heck is that? That's a sulfate ion. We can go to table E to know that. Okay, so this is going to be an ion, a polyatomic ion. Right away, I should know what charge this is. If I don't remember, let's look it up because they want to know what X is. So they're building a chemical formula. And when you build a chemical formula, the compound is going to be neutral. And I know it's neutral because I don't see any charges written here. So if I know the charge of this cluster, this polyatomic ion, okay, I can figure out what element this could become, because certain elements, based upon their number of valence electrons, can become that charge. So let's go to table E. So in table E, we have our polyatomic ions. I call this table the what the heck is that table? Because you'll see clusters of things that are not normal or not palatable to some people. Like if you see sodium and F, hey, that's sodium fluoride. It's binary. The naming system is IDE. It's two different elements, two different capitals. But if you saw what? Na2CrO4, like, whoa, that's too big. There's so much stuff going on. Well, it's really pretty easy. This part of the compound is -2. Notice sodium, you need two of them, each one is +1, and it makes sense. The overall compound is 0. And when you name a ternary compound, that'd be sodium chromate. This would be sodium fluoride, IDE, for just the ending of the second element. It's binary. So here, we're looking for the charge of sulfate. We're not naming, but we could have been. So I find my SO4, and I kind of gave it away, is the sulfate ion. And it's -2, and that's important because if I'm going to have X, some chemical, SO4, and just having one of them, that means, well, if this side, and I like to draw a line down this side from positive to negative, the positive is always first, this entire cluster is -2. So the whole thing to be 0, the X has to be +2. So the key to the entire problem is knowing that this cluster was -2, and this ionic compound or salt, if I'm just going to have one X, it's +2. Unlike what I have here for sodium dichromate, or I'm sorry, chromate, I needed two sodiums because each one was +1. All right, so this is telling me that my first guy has to be +2. So let's go back and look at our choices. Okay, so our choices are aluminum, argon. Argon, you should jump out and say, whoa, what's a what? That is a noble gas. These aren't very reactive at all. They typically have what you say 8 valence electrons, meaning argon has a filled octet already, so it's not available. None of these are available for bonding. You could get rid of argon. But what about aluminum, magnesium, and sodium? Remember, sulfate, we just figured out, is -2, this cluster. So the one in front has to be +2 to make the whole compound neutral. So which one becomes +2? Aluminum, magnesium, or sodium? Back to the periodic table. That will help us. So aluminum is one of our choices. If you notice, It's got 3 valence electrons. Because it's a metal, it likes to lose all of its electrons and become positive 3. You don't have to go to 3 here, but remember, if you want to find valence electrons, you can get rid of the 1 on this side, and it's a 3. Or look at the last number, it's the outermost electrons. But more importantly, aluminum likes to become plus 3. This is the charge it likes to become. And as we just said, we're looking for an element that comes plus 2. So aluminum is not one of the choices we'll pick. Now, if we go over to the other side where we have our sodium, sodium likes to become plus 1 because it likes to lose its outermost electron. So that's not a good choice. And then magnesium, and that's our winner here, likes to become plus 2 by losing its 2 valence electrons. So magnesium is the winner. And so magnesium 34 is choice 3. All right, 35. What is the chemical formula for lead? Whoa, Roman numeral 4 oxide. What is that? Okay, well, first of all, the IDE ending is screaming that I have a binary compound. So lead is, well, if you didn't already know, it is the symbol Pb. Now, all of your choices have Pb. Okay, so if you didn't know where to go for what the symbol of lead is, again, the most underutilized table is table S. Table S will tell you that lead has a symbol for Pb. So if you weren't sure about what the elements are, table S tells you that. Not a problem here because every choice has lead. Now, oxide is screaming that this naming system is binary. That means there's just 2 different elements, and ox is oxygen. The question is, what is the chemical formula? And why are they saying lead 4 oxide? Because if you said to me, hey, sodium oxide, you would know, okay, it's oxygen because it's binary, and sodium, and we know oxygen is -2. Sodium, if you look at the charge it likes to become in the reference table, upper right-hand corner, we just saw that for 34, is +1. So if you want to do the crisscross, you could, or just understand you need, what, 2 of these for 1 oxygen, right? 2 plus 1s would give me +2 overall for the positive one, for the 1 negative. So that'd be easy. Why do I need to have this 4 here? Well, the answer to that is because lead has multiple positive charges. Sodium does not. So elements that have multiple positive charges, you need to say which positive charge are we dealing with. Case in point, lead, okay, they're telling you not the 4th oxidation state, as a lot of students say. They're saying that lead is +4. So they're telling you we're dealing with the +4 charge. And the reason is lead, when you look it up on the reference table, lead likes to become +2 and +4. Unlike sodium that I just gave an example with, only becomes +1. So if you're dealing with elements like we are in this case that have multiple positive choices, then we use the Roman numeral system always for the positive one, never for the negative one, to say which positive choice we're using, because you'd make 2 different formulas. So they're telling us it's lead 4. Oxygen, upper right-hand corner of oxygen, is -2. And so, if you do the crisscross method, okay, you'll get what? Pb2, okay, right? Crisscross your charges. That's one way to do it. PbO4, and what you should know is that salts, ionic compounds, metals, nonmetals, what you do is you need to have an empirical formula. You need to reduce to lowest terms, because what this really is how many lead +4 ions are in a crystal of oxygen negative ions. So you got to reduce this. So this is going to become PbO2, and that is the answer. Now, what would the answer be if I had the other oxidation state? Well, the other oxidation state is +2, and this would mean lead, Roman numeral 2, oxide. All right, and I'm coming. And so lead Roman 2 oxide would mean that lead is +2. Exactly. And the oxygen is still -2. So if you crisscross and reduce the lowest terms, or see that the number of ions with the lowest whole numbers that gives you a neutral charge would be PbO. So PbO, which is not a choice here, would be lead 2 oxide. And again, the reasoning that we have the Roman numerals is to tell us exactly which positive oxidation state. It's always for the metal, the positive leading one, never for the ending one. So, of course, the answer is 1. This is typically a good part 2 question where they'll ask you to write the chemical formula. I've seen that. What can be a multiple choice question could also be a part 2. So working on your multiple choice, you're really working on the same skills if you understand the questions entirely. Number 36. Number 36. Which statement describes the general trends in electronegativity and atomic radius as the elements in period 2 are considered in order from left to right? Okay, well, if you look at the period 2 or row 2 elements, lithium, beryllium, boron, don't be one, carbon, nitrogen, oxygen, and fluorine. Okay, if you look at them, all right, you should know that the atomic radius actually gets smaller as we go across. You should know your nonmetals are smaller than your what? Than your metals, okay? And the reason being is that the atomic number is increasing, which means the number of protons is increasing, party people. Lithium has 3 protons, atomic number 3. This is 4, this is 5, this is 6, 7, 8, 9. So as we add more protons to the nucleus in the same energy shell, the attraction, okay, or the nuclear charge increases. So it pulls in the outermost electrons more and more. So you should know the atomic radius decreases. Now, the electronegativity is a word you have to know for this course, comes up all the time. You can bet your bottom dollar you'll see it. It means the attraction for other elements' electrons. And if you attract your own electrons really well and pull them in tighter, that's why fluorine's smaller than oxygen, and so forth and so on, then you're going to have a great ability to attract others. So attraction of other um, elements, electrons. Okay, it's very important. So as we add more protons and as we pull in our electrons in tighter and tighter and tighter and tighter, you have a greater ability to attract other people's or other elements' electrons, and your electronegativity increases. So the atomic radius decreases, okay? Because of the increasing number of protons called nuclear charge, and therefore your electronegativity increases. That's something you need to know for part 2. However, if you knew none of that, the most underutilized, okay, table is what? Table S. Let's go there because you can just read these values and see what the answer is. But the answer is choice 3. Electronegativity, the ability to attract other people's electrons, increases as you pull in your own, and your atomic radius decreases as a nuclear charge increases. And I'm saying nuclear charge, it's not part of this problem, but you have to know that for part 2. But let's go to table S to show you that this question is all about reading the table if you don't know your trends. So here we are in table S, and look what they give you. The symbol, the name, and look where we're going from lithium to beryllium to boron to carbon to nitrogen to fluorine. What's the atomic radius doing? Big, and it gets smaller as we go across the period because the number of protons, hello, is increasing. Hello. And if our atomic radius is decreasing from lithium all the way to, let's say, fluorine to neon, although I didn't write it there, what happens to electronegativity? Whoa, it increases as we go, as we get smaller, we attract other people's electrons more. Our ability to attract our own electron increases because the atomic number is increasing. Okay, means their electronegativity increases. So you can see that here. Electronegativity is increasing as we go across period 2. Okay, and if you didn't know that lithium to neon is period 2, okay, you can go to the what? The periodic table to see that. And of course, the atomic radius decreases. This is right off table S. Now, of course, you had to know lithium to neon is period 2. And again, that would be right from your what? your periodic table. And as you can see here, here's my lithium to beryllium, all right, to what? To boron to finally fluorine to neon, okay? So the attraction for other people's electrons or electronegativity increases as the atomic radius decreases. And both of these properties are properties for what? Nonmetals. High attraction and small radius. Number 36 is 3. Number 37. Number 37, what is the percent composition by mass of nitrogen in ammonium, that's NH4 cluster from table E, carbonate? If I was naming this, I'm just naming the clusters from table E. This is the ammonium, it's +1, and this is the carbonate cluster, -2. Notice I need 2 of these +1s. Now, percent by mass, okay, is essentially part over total times 100. And of course, we're going to use mass. Now, what do we do to get the part? Well, they're asking for the nitrogen. So we got to find how many atoms of nitrogen in this compound. Now, because we don't have any masses, nothing was measured like an experiment, we're going to use and assume, okay, 1 mole. We assume 1 mole of a compound, and we should know 1 mole of a compound is equal to the gram formula mass, which means if I was to add up the individual elements' atomic masses, okay, that would give me the grams per mole. Guess what? They gave me that. So this is the mass of 1 mole of this compound, okay? And if you don't have that, I'd have to do what? Basically go into my reference table, figure out the mass of an oxygen, times it by 3, the mass of carbon, add the 1 to that, 2 times 8, 8 H's times its mass plus the mass of nitrogen. There's 2 of them there because of the 2. We'll talk about that. So they already gave me that. So I don't have to figure out the gram formula mass. It is 96. But they're asking for nitrogen. And the easiest mistake to make is, oh, well, 1 nitrogen, let's go figure that out. But careful, there's a 2 here. There's 2 of everything inside. So we have 2 N's. Let's go to the reference table to see what the atomic mass of nitrogen is. And nitrogen is 14.0067. This is the atomic mass. We know it has a decimal place because it's the average of all the isotopes, including their relative abundances. But we just round this off to 14 when we do this because we just can use the what? The most abundant isotopes. So round this to 14. So 1 mole of nitrogen is 14 grams. Okay? So each one is 14. We have 2 of them, though. Don't forget that not Roman numeral, but that subscript 2 means 2 of everything inside. Like if I wanted hydrogens, it'd be 2 times 4 is 8. 2 times 1, so it's 2 nitrogen. So it's 2 times the 14, and that's going to equal 28. And that 28 is the part that they were asking for. They said the percent by mass of nitrogen in that. Okay, we're assuming 1 mole, so the grams for 1 mole is 96 grams. And if I have 1 mole of this, one of these, there's going to be 2 moles of N. Okay, so it's this 28 divided by 96 times 100. Okay, and you put that in your calculator. So simple. To put the part 28 divided by 96 times 100, and it's about 29.2%. And that's the reason for choice 2 being the answer. Now, very easy for you to put 14. Now, if you put 14 over 96, you would have got 14.9% because you said, oh, 1N, it's just nitrogen, and it's easy. So this question was built for you to get trapped into using 1 nitrogen and forgetting there's a 2 there. Okay, so very classic math question. This clearly could be a math question in part 2, seen it many times. And sometimes they give you the gram formula mass, which is the mass per 1 mole. That is the total. Sometimes they don't. And sometimes just asking and coming up with the gram formula mass is a problem by itself. And again, although that wasn't the problem here, you would have 2 N's, right? You'd have 8 hydrogens, and you'd have 1 carbon, and if I keep going, you would have 3 oxygens. And of course, I already did 2 times 14. There's 8 of these. 8 times the atomic mass of hydrogen is 1. There's 1 carbon times the atomic mass of carbon is 12. And then there's 3 oxygens. 3 times the atomic mass of oxygen is 16. And all of these numbers that I am using here are from the periodic table. They're the atomic masses for each of these elements. I find these numbers and I add them together, and that number that I add together would come out to approximately 96. And that could be a problem in of itself. So number 37 is choice 2. Number 38, given the balanced equation, chemical reaction, what type of chemical reaction does this equation represent? Now, if this was in part 2 and I've seen this, the first thing I look and say, well, I know most reactions are redox, and I've taught you to identify a redox reaction, find yourself a 0. Now, what's a 0? A standalone element. Whether it's standing alone by itself or bonding to itself, it's still an element. So there's 2 zeros here. Find yourself a 0. So you could say in part 2 that this is a redox reaction. And how do I know? If I have a 0 on one side, that means it's not a 0 when it's bonded to something, right? So that's important. You can sign oxidation numbers and see that they're changing too. Okay. Bottom line is these oxidation numbers are changing. Electrons are being passed around. Someone's losing. That's oxidation. Someone's gaining. Now, unfortunately, in this question, although this would be acceptable in part 2, they're kind of closing you in on the choices you can use. So it's not so wide open in part 2, and that's why part 2 should be easier. I know people are always scared of it, but it's the same concepts as the multiple choice. So what do we have here? Well, we have an idea where the K, okay, or the F is replacing the iodine here. Okay, and because it's not double replacement, because you don't have 2 things here, it's a single replacement, which, by the way, is a classic redox reaction. Very classic redox reactions are single replacement reactions. So it's not synthesis. Synthesis would be if we take elements, right, and we put them together to make something. So small pieces making bigger. Decomposition would be the opposite, right? Taking something like AB and breaking it down into its individual elements, A and B. Double replacement would be the classic example. Let's say we have lead nitrate. That's a lead 2 nitrate, let's say, and Ki, and then we're going to double replace. Remember, the positive ion is in front. This would be positive 2. Nitrate's a negative ion. This is positive 1. This is negative 1. So we're just going to basically, what? Do-si-do, switch our partners. If you're into square dancing, I hope you're not. Lead iodine, so that's going to be Pb is plus 2. Iodine's negative 1, so you'll need 2 of them, right? And of course, we're going to have KNO3. K is plus 1. NO3 is that polyatomic cluster. And table E is negative 1. Now you don't need the charges. I'm just writing them to show you that the charges are not changing. It's not a redox reaction. So there's double replacement. There's 2 things. Remember, this lead now is going with, okay, this I, and this K is now going to go with this KNO3, and we write the positive ion in front. Okay, so in any case, single replacement is a single replacement going on, not a double, and that's classic redox. So 38 is choice 3. Number 39, which form represents a nonpolar molecule containing polar covalent bonds? Whoa, I love this question. Okay, nonpolar molecule is going to be a molecule. Okay, it's a molecular compound. It has a definite shape, and it's going to have more electron density on one side of the molecule than others. So I don't know why that just happened there, but I'm going to have more electrons on one side, okay, than others. And so the electron-rich area is given the negative sign, and the sign that has less electrons is given a positive sign. And these are partial positives and negatives. But nonetheless, it makes the molecule polar. It's got a more negative side and a less negative side we call positive. Now, what creates that? Well, normally polar bonds. bonds that share electrons unequally and pull them to one side and have a difference in electronegativity. But if we're a nonpolar molecule, normally speaking, it's because we have symmetry. Okay, so look at CO2. CO2 is very symmetrical, meaning that both sides are the same sides. So this is also very symmetrical. These are asymmetrical. Okay, and what we've learned is if it's an asymmetrical molecule, there's going to be asymmetry or an unequal distribution of electrons around a unequal symmetrical shape, and these will always be polar, okay, if the bonds are polar. So these are polar molecules, okay? They definitely have a negative end and a positive end. Okay, now these are nonpolar because of their what? Very symmetrical symmetry there. Now, so which one has polar covalent bonds? Well, polar covalent bonds means that we're sharing electrons unequally because of two or more different atoms. If you look at H and H, pulling this out, here's hydrogen, and a little lag here. It has one valence electron, and I have another hydrogen. Lag is killing me here. And it has another one valence electron. Trying to draw an X here. Thanks, guys. All right. Now, these pair of electrons, because hydrogen has 2.2 electronegativity, which, by the way, I'm getting that from table S, and this one has 2.2 also. Crazy. How can that be? Well, it's the same element, same attraction for other people's electrons. So this is 2.2 as well, even with the lag. All right. So because they are the same element, and of course that means the same attraction for these electrons, they're going to be shared right down the middle. So one side of the bond doesn't have more electrons than another. So guess what? This is going to be a non-polar. Okay, I can do this with the lag. Non-polar covalent bond because they're the same element. And for reasons we just explained, O and C have two different electronegativities. If I was to draw this over here, just draw one side, double bond means there's two pairs of electrons, but these two pairs of electrons are getting pulled closer to the oxygen side. Why? Because oxygen is much more electronegative than carbon. It's a higher number, so it's going to pull this over, and this side of the bond is going to be more negative than this side. So it's unequal sharing, and sometimes they ask for which one is unequally shared, and that creates an electron-rich area on this side of the bond, and polar means having differences. So 2 is the answer. It is a nonpolar molecule because of its symmetrical shape. Its electrons are then going to be evenly distributed, which means one side or the other doesn't have more electrons, so there's no difference. But having a polar covalent bond means you have two different nonmetals with two different electronegativities, which means they're going to be sharing unequally. So the 2 is your answer. Okay, now just so you know, water has two polar covalent bonds too, and so does ammonia. They have 3. So they definitely are sharing unequally, but because of the asymmetry, there's definitely, like if you look at water, look at its shape, because the oxygen here on the top is pulling electrons more, most of the electrons are going to be next to the oxygen. So this is the negative area, and this is the place without the electrons. And there's what the asymmetry gives an opportunity to have an unbalance of electrons or poles. Okay, so number 39 is 2. Number 40, a reaction reaches equilibrium at 100. The equation and graph representing the reaction are shown below. Okay, great. Now in this famous graph, what do we see? Concentration versus time. What we see is the concentration of N2O4, which by the way was the what? Was the reactant, and you notice you're starting pretty high. And the product, NO2, you're starting with 0. That makes sense. So over time, there's a buildup of the product, and over time, the what? The reactant goes down. But something special happens right here and right here. And what's happening is at that point, the concentrations, the molarity, stay constant. Okay, the the amount of products stay constant, the amount of reactants stay constant, and that is the key to the entire graph. I have seen questions in part 2 where they say, I've seen this graph, and they basically ask the opposite question. So let's go to the questions. This should jump at you. The graph shows that the reaction is at equilibrium. Boy, I'll tell you, that's really giving it away after 60 seconds. Well, after 60 seconds, something stays what? Something special happens, because the concentrations are what? Are constant. The line stays constant. Even if you didn't even have the graph, there's two things you should know at equilibrium. Number one, the rate of the forward reaction equals the rate of the reverse reaction. If that is true, we write double arrows, then the amount of reactants and products stay constant. Okay, so if you didn't know anything about the graph, but you knew the equilibrium, you had to know that the rate of the forward equals the rate of reverse, or because of that, the amount of each stay constant. And if you don't see that, if I have 2 people on this line, and then I have, let's say, 5 people on this line, and I ask one person from each line to switch lines every minute, come back 10 minutes, although the people will change, I'll still have 2 people on this line and still have 5 people. The amount of reactants and products stay constant if the amount of products becoming reactants equals the amount of reactants becoming products. So number 40 is 3. Key points in equilibrium. The reactants and products stay constant, and the rate of the forward equals the rate of the reverse. Number 41. Okay, number 41. Given the balanced equation representing the reaction, which statement describes the changes in energy and bonding for the reactant? Okay, well, the first thing that I come to look at and jumps out at me is that the energy, which could be written as heat, is written in front of the arrow. That means it's going into. Okay, this is the reactant side. Okay, and these are the product side. So when I see the heat written on the reactant side in front of the arrow, that means the heat is going into the arrow. See that energy is going into, and this screams to me, okay, endothermic, because energy is going in, and as we know, endothermic is energy is being absorbed, or I like to say consumed. It's being used for something. Okay, so the thing as I jump out to me is number 1 and 2 could be the answer, because energy is absorbed, because the heat is written on the reactant side. Now the question is, are the bonds broken or formed? Well, we know, okay, that H2O2 is going to make H2 and O2. Now in order to make products, okay, in order to make new products, which is what a chemical reaction is, these bonds have to be broken. And we should know to break these bonds, we always need energy. This is not a great problem, okay? But it's understandable that we can figure out, because the energies on the reactant side, it's endothermic, which equals we're absorbing energy. The reason why it's not a great problem is because when we talk about the changes of bonding, in order for water, okay, and 2 of them to become 2 H's, right, 2 H2s and 1 O2 that's double bonded, okay, we can all see what's going on here. These 2 H's would come and form a new bond, and these 2 H's would form new bonds, and that's how we get there. But in order to form new bonds, we have to break the bonds first, and breaking bonds requires energy. I know the energy is written there. Okay, I don't love this problem, because no matter if the reaction was endothermic or exothermic, breaking bonds is the first thing that we do for all chemical reactions, and breaking bonds always requires energy. This energy that's written, guys, is the overall energy change. And let me explain this to you so you understand. Okay, this reaction is endothermic. Okay, great. And that means that energy overall is being added. So we're starting low and going high, and that's our potential energy curve. There's our endothermic, and you should know that, party people, because the difference of where you start and where you finish is your delta H, and our delta H is positive because we're going up in energy, because we're overall absorbing energy. But you should be aware that it takes energy to break bonds. What I mean by that, party people, is that the energy to go from here to here is the energy it takes to break these bonds. Before I can form new ones, I have to break bonds. So these bonds have to be broken first, and it always takes energy. Why? Because bonding is a stable state. If you look at water, it's got 6 valence electrons, or I should say oxygen does. Okay, oxygen, if you look at the reference table, is 2-6. It's got 6 valence electrons on the outside, 2 in the filled kernel held closer. These are unstable. Hydrogen has 1 valence electron. So by bonding with 2, everybody feels like they have a stable amount. By sharing 2 more, oxygen now is 2-8. By H sharing 2 more, right, it feels like it has 2 electrons like helium, and oxygen feels like it's sharing 8. So bonding, and this is important, bonding is equal to a very stable, and stable means low energy state. The reason why atoms bond is because they want to achieve stability. The same reason why you want to put your feet up on the end of the day and relax after a busy day is because you're tired. Okay, at the end of the day, we want to be low energy. Well, I know that atoms aren't alive, but at the end of the day, they want to be energy. So the reason why atoms bond are to get stable. Remember sodium, this is ionic now. Sodium, okay, has 1 valence electron. It's 2-8-1. Well, guess what? If it could lose it, hey, now it's as stable as 2-8, the octet rule. Oxygen gained 2, okay, by sharing in this case, to have that 8. Okay, now chlorine, we know, just like fluorine or any halogen, they have 7 valence electrons, sorry. So they can actually take this and have 8, and they'll become a negative ion, and sodium will now become positive, and that's how ionic bonds happen. But if chlorine, which is 2-8-7, which I'm getting from the reference table underneath the element, it needs to gain 1 to get that magic 8. Okay, the only difference here is hydrogen only has 2 electrons in the first energy shell, right? So it already has 1. By gaining 1 more, either by sharing or transferring, if it's ionic, can be stable. So if things are already stable, low energy, guess what? You need to add energy to the system to break them. Okay? Now, once they're broken, and that's what this is about, energy absorbed as the bonds are broken. And this would be right, even if this energy was on this other side, but they're just trying to play games, I guess. 2 is the best answer. They're trying to make a very simplified answer. But anytime you break bonds, and again, it probably will not be written this way. It's a poor question because they're mixing some ideas here. But anytime you break bonds, energy must be absorbed endothermically to break a stable state that's already low energy. Okay, to make them into this state where they're free atoms up here. And then, guess what? To form the new bonds, guess what? Bonding is stable, low energy. You're going to have to release energy, okay, to become that. Now, the reason why it's overall endothermic is because more energy was needed to break these initial bonds in water, which are very stable, than the energy released to make these bonds here in these elements, these diatomic elements. Bottom line for this question, energy is always needed to break bonds. If you think with me, if you want to break anything, it takes energy. And you should know this, although it's not part of this question, but it will pop up on your test somewhere. Forming new bonds, energy is always released. Okay, why? Because you're creating a low energy state. Anytime you go to a low energy state, energy must be released. 41 is 2. Number 42. Number 42, at standard pressure, which we should know is 1 atm. If you go to table A, they give you STP, standard temperature and pressure. But in any case, it's 1 atm or 101.3 kilopascals. Okay, so in any case, What is the temperature at which a saturated solution of ammonium polyatomic ion chloride has a concentration of 60 grams in 100 grams of water? This is screaming, okay, table G. Because what is the giveaway for me is the saturated solution. And I know at what temperature at which a saturated solution, if it's saturated, party people, I know on table G, which is a solubility curves, okay, for solids and gases, solids going up, gases going down, I am on the line for a particular temperature. Now, what temperature at which a saturated solution has a concentration of 60 grams in 100 grams of water? Well, this graph on table G is based upon 100 grams of water. So be careful with how much water you have. If you have 50 grams of water, normally you may have to make an adjustment based on the problem. All right. So half the water, usually half the solubility. Okay, so normally you can cut that in half. If it was 200 grams of water, you could usually double that. But in any case, it's 100 grams of water, so it's as base. Now, 60 grams. So you're going to have to find on the y-axis, they measure, you'll see different grams, a graduation of grams. That's the grams of the compound. So this is the curve for ammonium chloride. And I don't know what it looks like perfectly, but I'm going to go find the 60 gram mark, and I'm going to go over until I hit the line, and then I'm going to go find that temperature at which it's what? Saturated on the line for that much. It tells me, notice at a lower temperature, this is temperature down here, less of it will be saturated. Remember, solids, you can dissolve more of it if the water is warmer. So I'm looking for 60 grams on table G that'll be on the line. And what is that temperature for ammonium chloride? Let's do that in table G. So here we are in table G, one of my favorite tables, and it's a solubility curve, and I knew I had to be there because of some definitions. Saturated is on the line for particular temperature in water, under, saturated is under, and super is above. So that's saturation, and give me all that information about how much water. Notice on the left-hand side, okay, where it says solubility, that's the ability of the water to dissolve these compounds. It's based upon 100 grams of water. So it's in 100 grams of water, and this is grams of solute. So this is how much. So our magic number is 60. They said 60 grams. What temperature is ammonia chloride soluble? And so ammonia chloride is this line right here. It's really sometimes beneficial to just kind of mark what line you're working with. Obviously, you don't have this kind of a marker, but it gets confusing with all these lines. Ammonia chloride, this is the ammonium ion, table E, and the chlorine is chloride. And so where is it on the line? So if I have 60 grams of my solute, which is ammonia chloride, in 100 grams of water, where does it cross the line? Right there. And what is that temperature? Straight down. Of course, I'm having a tough time drawing straight lines. So we can probably guesstimate it's somewhere 67-ish, 66-ish. Okay. And let's go see what our closest answer is. Okay, so that's what we're looking for, the temperature at which 60 grams of it will dissolve maximally in 100 grams of water. Table G question. So I'm getting about 67, 66. Let's see what the multiple choice question has. And there it is, choice 1, 66, the best answer. Okay, so 42 is 1, and this was a table G question. And the reason to know it gets experience is that they're giving you how much water. They usually have a temperature involved, because they're looking for the temperature here. They give you the grams of solute. But the key for me right away, once I said, oh, they want a saturated solution, boy, that's key. Remember, on the line is saturated, under the line for particular temperature is unsaturated, meaning you can add some grams to get there, and above the line is super. And those words can usually give it away for me with the extra information. 42 is 1. Number 43. In number 43, which aqueous solution has the highest boiling point at standard pressure? Okay, so boiling point, and we're basically, it's a solution, which means it's a mixture of this solute dissolved in water. And what we're trying to answer, if this water for aqueous means it's mixed with this solute particle. Now we need to understand that's called colligative properties, and it's a type of property which is dependent upon how many particles are getting in the way of the water. See, we know water boils at 100 degrees Celsius at standard pressure. In fact, table H shows us that how vapor pressure and temperature changes. Now, when you add solute particles, they get in the way. So if I've got myself a container and I've got the fluid level here that's basically where the water can leave from, and we have, let's say, water molecules. I'm just going to make circles here for water molecules. And we know that water molecules attract each other by H bonding or intermolecular forces of attraction. Okay, so they're holding on to each other. And of course, there's many of them, and I'm not drawing nearly as many as I should, but the point is that if a molecule has enough energy and it can overcome these attractive forces and gets to the top of the liquid layer, it can leave as a gas. Okay, now what do we know is that if this happens and the atmospheric pressure is constant, so let's just say the atmospheric pressure represents my black arrows pushing down. So when I have this pressure that's pushing down on the liquid, that's there, it's atmospheric pressure. And if I have enough heat that's absorbed by the system, this could be a Bunsen burner, it's my nice flame, okay, and enough of these particles can overcome their attractive forces and get to the surface, then what can happen is the vapor pressure, which is the force due to liquid molecules evaporating out of the container, okay, equals the pressure pushing down. We have ourselves a boiling point. That's the temperature by which the vapor pressure upward equals the atmospheric pressure. Now, atmospheric pressure is nothing more than gas molecules randomly moving and hitting downward in the downward action. So when these pressures are equal, we have boiling, which is essentially maximum evaporation. So that's true. So the vapor pressure at 1 atmosphere pressure, that's when they said standard pressure. So let's make the pressure 101.3 kilopascals. Okay, so the vapor pressure equals 101.3 kilopascals. When the atmospheric pressure is 101.3, I should write it right over here. So 101.3 kilopascals, the unit of pressure. So if the atmospheric pressure is 101.3 and we increase the vapor pressure enough to equal that, we've got boiling. And of course, we have to add heat to make the liquids overcome their attractive forces and get to the surface and basically move upward to do that. Now, the key here, party people, is that we're going to start adding solute particles. So let's make solute particles, let's say magenta. Hey, why not? And so I'm going to add some solute particles. Now, if I add solute particles, and these are things that do what? These are particles that get into the water because they have similar attractive forces. We learned that like dissolves like. Okay, so these would have to be polar molecules, or they'd have to be ions who have a positive or negative side that water can attract to, because water is polar. And so what do we know, party people? Well, these solute particles, which are going to be soluble, and in this case they're all going to be ions that are positive or negative, are going to do what? Well, they're going to get in the way. Look at this solute particle is now going to block this guy, and so this pressure doesn't occur anymore. In fact, the vapor pressures, you can see how the solute particles are going to get in the way. They're going to be basically a physical barrier for these molecules to get to the surface. So if that's the case, the vapor pressure is going to drop at a particular temperature. And we're going to need even more temperature or even more heat and raise the temperature high enough to create a bigger vapor pressure. So the boiling point is elevated every time we add solute particles and have a solution. That's something you should know. In fact, I tell my students the 2 thumbs rule. Here's a thumb going up, and then we have a thumb going down with fingers going down. And the higher temperatures, boiling point elevates, freezing point decreases as you add solute particles. How do you know? When you make an aqueous solution, these particles now are getting in the way. And the more they get in the way, the more that they lower the vapor pressure, and then the more heat you need to overcome these obstacles. And therefore, the boiling point is going to be raised higher, meaning you're going to only make the vapor pressure equal the atmospheric pressure only when you give the water molecules more energy to overcome these obstacles. Okay, that should be clear. All right, so the question is, who is providing which solution? They're all aqueous, they're all dissolving, and how I know that because they're all written as aqueous, but which one written here, okay, is going to provide the greatest number of particles? Well, I look at 1 molar and I look at 2, so I'm kind of looking at probably between 3 and 4. Now, how do I know how many particles? Well, look at KCl. KCl, you should know, is an ionic compound that in water, because it has a positive or negative and is soluble by table FUFU or table F, anything with a group 1 ion is soluble, breaks apart into K plus and Cl negative. So this breaks apart into 2 ions. Calcium chloride. You should know that calcium chloride is also ionic, metal, non-metal, but this isn't Cl2 bonded. It's a calcium plus 2 and 2 chloride ions. Remember, chlorine gains 1 apiece from the 2 that calcium loses. So this is going to make 3 particles for the same molarity. So if I look at 2 things, the first thing I look and see is, well, the molarity of these 2 compounds is greater. So that means you have what? What's molarity? It's the moles of the solute, how much you have over the liter solution. Since these are both the same, okay, 2 molar of KCl is going to have more particles than 1 molar KCl. And then if I look at choice 2 and 4, 2 molar calcium chloride is going to be more concentrated in more particles than 1 molar. Now, these guys being even, because calcium chloride breaks apart into 3 particles, it's as if, take this 3 and times it by 2, it's as if it's 6.0 molar. How did I do that? Well, if it's a 2 molar solution of calcium chloride and one of these breaks apart into 3 particles in water, then it's as if it's 6 molar. So because calcium chloride breaks apart into more particles than potassium chloride, and it should be clear to see how that happens, at the same concentration, calcium chloride is going to get in the way of water more. So calcium chloride is going to have more of these particles that are in the way, and therefore lower the vapor pressure, which means you're going to need more heat. So the one that's going to have the highest boiling point is the one that produces the greatest number of particles. So in this answer, you have 2.0 molar is the highest concentration, the greatest amount of mole. Mole represents the number of particles. And this formula that's ionic is screaming to you that there's 3 particles given off. So for 2 reasons, 4 is the answer. It produces the greatest number of particles. Higher the number of particles dissolved, higher the boiling point. Now they could have asked the same question and said, which of the following has the lowest freezing point? It's called freezing point depression, and it'd still be number 4. Okay. All right, so 43 is for a nice colligative property question. Number 44. Number 44. Given the equation representing a system at equilibrium, which change causes the equilibrium to shift? Ooh, shifting equilibrium. This is screaming to me Le Chatelier's principle. They want to know which of the following stress will cause the reaction to shift. Now, shift would mean that it's going to go faster in one way or the other. If it's at equilibrium, you should know that the rate, the speed of the forward reaction equals the speed of the reverse. One of these choices is going to disrupt that balance and make one of the ways go faster than the other, which means it'll overall go forward or reverse, left or right. So let's go through the choices. When I do Le Chatelier's problems in shifting of reactions, I like to do stress and then response. The response is what the reaction does. And as I explained over and over again, a reaction wants to be at equilibrium. Everything moves toward equilibrium. So it wants to regain its balance. So if I have a person, okay, and this is my poor drawing of a person. This is me. You can tell it's me with a tremendous amount of hair. Now, this person, of course, is happy, okay, and I guess 1 eye. And we'll just keep it that way. Now, if I was to push this person, me, I'm going to fall over unless I push back on the back foot to regain my balance. So whatever I do by putting a force, I'm going to have to push the opposite way on my feet to regain my balance. Reactions do that. You give them a stress, they're going to respond by doing the opposite to regain their balance. Okay, so the reaction's response is always going to be the opposite of our stress so that the reaction works toward equilibrium. That's a really important thermodynamic principle that we'll learn in more advanced chemistry classes, that reactions always work toward equilibrium. All right, so let's the first one, increasing pressure. So if I increase the pressure, what's the response by the reaction? To lower the pressure. Now, when we deal with pressure, we count moles of a gas. And this is a solid. This is an ion dissolved in water, aqueous, and this is an ion dissolved in water. Because there are no gases in both sides, if we were to have a pressure stressor, okay, we would always, if the reaction has too much pressure, it would shift to the way, left or right, to lower the pressure by going to the side that has less moles of a gas. Because there's no gas on either side, 0 moles of gas on this side and 0 on this side, this has absolutely no effect. So therefore, this does not cause a shift. Okay. Now, if we look at the choice 3, and you probably know why I'm jumping around, but if you do choice 3, and I'm just going to get rid of this, don't know why that was doing. So if we look at choice 3, adding a noble gas. Well, a noble gas, first of all, doesn't react with anything, but even if it did react with something here, the noble gas doesn't affect, I should really say the noble gas does not affect the ions or the reaction. So the noble gas, which has no reactivity, okay, will have absolutely no effect because it doesn't react with any of the reactants or products. So that would cause also no shift. Adding a catalyst. Well, we should know that when we have a reaction, let's just pretend it, let's say as it's written, that's endothermic, right? Starting low and going high. The delta H is positive because energy is being consumed, or energy is being absorbed, either way. So this is going up, this is delta H, and it's positive. If I add a catalyst, you should know that it changes or makes an alternative pathway, or it lowers the activation energy. But you notice, even though it may lower this hump, as I like to say, medicates the hump, it doesn't change where we start and where we finish. So therefore, adding a catalyst, okay, doesn't change delta H, and it lowers, I should really say, it lowers the activation energy for the forward, and it lowers the activation energy for the reverse. So it does it for the both. And so a catalyst is not going to cause a shift. It'll make you reach equilibrium faster if the reaction is not. So the best answer would probably have to be 2. Let's see if we can figure this out. 2, if I increase the temperature, the reaction is going to look to decrease the temperature to regain its balance. Now, since energy is on the reactant side, increasing the temperature, the reaction wants to shift to lower the temperature. So we're always going to favor, okay, if we're trying to lower the temperature, we're going to shift to the right to use up the energy. Okay, so we have too much heat, so we're going to favor the endothermic pathway, which is the forward reaction. Anytime you increase the energy, the reaction shifts to lower the heat. And you can treat energy like a reactant. So there's too much energy, so the reactant's going to shift to use it up. So the energy gets used up, the reactant gets used up, and you make more of the products, and they would build up as these guys drop, as the reaction shifts to the right as a response. Okay, that's the shifting does this, but we initially increase the temperature. Okay, so the best answer is 2. The rest of these choices will not cause a stress. Number 1, because there's no gases. Number 3, because noble gases won't react with any of these things, and it's not a common ion, I should say. There's no common NO2 here. And adding a catalyst will increase the forward reaction and the reverse activation energy, so that will not affect equilibrium. So 44 is 2. Number 45. Which hydrocarbon is saturated? Saturated means that the hydrocarbon, which is just hydrogen and carbon, careful, sometimes choices have oxygen, so you want to pick a choice that just has hydrogen and carbon. Of course, all of these do, but just trying to help you for future questions that are very similar. Now, saturated means for hydrocarbons that we have the max number of H's possible. And the only way that can happen if carbon is single bonded. If carbon is single bond, there is more room for H's. Remember, carbon has to make 4 bonds because it has 4 valence electrons, and it needs to have 4 bonds so it can reach the octet. So if there's a single bond between the carbons, then there must be hydrogens donating an electron to that pair to make that satisfied. So if you're going to have a 2-carbon molecule, you're going to have 6 H's. Now, there's a general formula that shows that in table Q. Let's go there. So in table Q, my friends, we have different types of hydrocarbons. You have alkanes, alkenes, and alkynes. And the most saturated of all of them, the one that holds the maximum H's because the bonds between the carbons are the fewest, are the alkanes. So if we're looking for something that is saturated, we're looking for an alkane. If you notice, the ones below it have double or triple bonds, and because carbon must make 4 bonds, there's less room for H's. Okay, so the more multiple bonds you have between the carbons, the less H's you have. So I'm looking for this formula that has the maximum number of hydrogens. So I'm looking to see CnH2n plus 2. Let's go back to the problem. So bringing back our formula of CnH2n plus 2, which of the following fits that scenario? Let's look at choice 4. Might be the answer. If I have 4 carbons, and then I'm going to have 2 times that number, 2, and it's 8 plus 2, that gives me 10. So this is your answer. There's no other choice that fits that formula for an alkane. And you can draw it too. 4 carbons, single bond. We have to have single bonds between the carbons to have the maximum number of H's. And if you count carbon having 4 bonds apiece, you can count the carbons. 4 carbons, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's, and that's how you can do it as well. The rest of these, okay, will have to have a multiple bond between them. Notice C4H6 has less H's, okay, so that must have a triple bond somewhere. Or in any case, choice 4 is the answer. The best way to do this is either draw it to see which one has single bonds, but you have to realize single bonds between the carbons. Okay, and table Q can help you with these formulas. Number 46. Number 46. Which volume of 0.600 molar H2SO4, H in front, screaming to me acid, exactly neutralizes 100 milliliters of a 0.300 molar barium hydroxide, metal hydroxide? That's a base, acid-base neutralization reaction. So one thing I will tell you is if you can identify acids and bases and they're adding them together, you're dealing with a titration problem. And a titration is basically a laboratory procedure where we use the information of one chemical. For instance, in this case, we know how much volume of this base and its concentration, and using this information we're going to solve for how much of the acid we need. So in using a standard piece of information that's given to us, we can answer questions about the other. So that's really what a titration is, but this is an acid-base titration, and these are what you do in Regents. So to identify it, I have a couple different ways to do that. The first one, if you see big M, and big M stands for molarity. And molarity, of course, given to you in table T, is moles of the moles over the solute over the liter of solution, and that equals big M. So the word big M, molarity, or even the word molar, okay, are all kind of synonyms here for concentration. Now, when you have a concentration and you see big M, and you see three variables. And when I say by three variables, I mean you see, hey, I have a concentration of one chemical, I have a volume of another, and a concentration. There's three variables right there. When I see three variables and I see big M involved, okay, I know that I'm going to deal with a titration problem. So if I see big M and I see that there's three of things, it doesn't have to be one volume and two molar concentrations. It could be 1 molar concentration and 2 volumes. But the bottom line is I see three different numbers and I see big M. 99% of the time, it's a formula called a titration formula, and it's going to be MV of, let's say, the acid, because I could do base first, equals MV of the base. Now, if I don't know this formula, but I know that I have it in table T, okay, let's go see, and so I can show you where you can remember to go to if you forget the formula. Here we are in table T land, the last page usually of your reference table, and I scroll down and I will see there it is, titration formula. And notice it has MV, the molarity, it's their big M, okay, which by the way, again, there it is above molarity, moles of solid-liter solution. So in this formula, okay, again, if you have three variables, okay, and what could those variables be? It could be molarity, volume, and molarity, and you're solving for the volume. That's the case that we're solving here. We have the molarity of the acid, the concentration. We have the volume of, I'm sorry, in this example, okay, we actually have the molarity of the base and the volume of the base. You're trying to find the volume of the acid. It doesn't really matter, but if you know your algebra, in our case, we're trying to solve for this. That means in order to solve for the fourth variable, we have to know three variables. So that's how that works. So it doesn't matter which one it is. In this case, we're solving for this V, the volume of the acid, knowing, okay, information about another chemical. That's what a titration means, is that you're using the information of one chemical, in this case the base, to answer something about the concentration or volume of the acid. And so you can see what they give here is what this represents. Now, as I show you other problems through my other videos, there are going to be problems where you have molarity questions, which by the way is equal to big M, that doesn't have three variables. Notice how many variables are in this problem. There's molarity, there's moles and liters. So there are three variables in this problem, and if you were to solve for one of these, okay, you'd have to know what? You'd have to know two of them. So if you've got a two variable big M problem, and how you know it's a big M problem, you'll see the word molar. You'll see what? Big M, okay? Or the word molarity. They're all what? Synonyms. So if you've got a two variable problem, you can solve for the third. If you've got a three variable solve, you solve for the fourth. So a three variable problem is this one here, okay? And so we're going to use this formula and go back to the problem. So as I said before, we're trying to solve for the volume of the base. So that's my X. And I'm going to leave it as V to remind myself that I'm solving for volume. What's the molarity of the acid? Well, H2SO4 is an acid. And you say to myself, well, how do I know it's an acid? Well, when you put an H in front, it screams acid. But if you don't know that, if you go to table K, it lists all of the common acids you'll be seeing, and this is listed here as sulfuric acid. In any case, the concentration is 0.600. That's my molarity of the acid. What about my base, barium hydroxide, which is again listed? This is going to be table L now. I can list some bases, but bottom line is metals with hydroxides. So this is going to be 100 milliliters for my volume. And of course, my molarity is going to be 0.300 molar. Now, there is one little catch here. 90% of the time, this is all you have to do. But there's a little bit of a catch here. This base, and let me rewrite it, is barium hydroxide, OH2. Okay, OMG, yeah. Because there's two hydroxides here, okay, it changes this formula a little bit. The reason why the acid equals the base. You may say, well, I'm not really quite sure why that works, and this makes you understand this problem more, so just give me a second. What is molarity again? If you do molarity of the acid, isn't it moles over liter? Yeah, and if we're using liter, and we don't have to for this formula because they'll cancel, but if you put liter here, you can see that molarity, not moles, molarity times volume, which is really what? Molarity is moles over liter from table T, times a liter as a volume. You can see that the liters are cancel, and this whole expression equals the moles of the acid. And if you do the same thing, which is the mole over liter, that's what molarity, big M, stands for, times a volume that's a liter, you can see that the liters cancel. What it means is the moles of the acid equals the moles of the base. That's why it works. Now, what's in the acid? Oh, well, there's H pluses, okay? And there is OH minuses. So what we're really doing here is we're saying the H pluses of the acid moles equal the hydroxides of the base. That's neutralization. We're taking an H plus from an acid and a hydroxide from the base. We neutralize each other because by themselves in high quantities, both of these can make a solution very dangerous. It makes water. Okay. Now, what we have to be careful of is that acids and bases can be, in this case, give off two of these. Look at this. Barium hydroxide gives off two hydroxides. So there's two here. Now, this acid is diprotic. It has two H's. So it just winds up that these guys will be equal. So in this case, we don't have to do anything. We can just solve for V, but you have to take particular care. Let me erase what I wrote here so you can see this clearer. So what I want to show you is, again, this acid has two H's. This base has two hydroxides. So this will equal each other. So there's nothing extra we have to do. But I just want to remind you that there are times where they could have given you another acid. What if the acid was not H2SO4? What if the acid was HCl? And there's just one H to two hydroxides. In that case, what you would do is you would put the number 2 down here. And because this only has one H, if it was HCl, I'd put a 1 here. Okay, and you can see that there's twice as many hydroxides, and that's how you would solve the problem. Okay, now if you have H2SO4 like we have here, you can put that 2 down here, but as you can see, that would just cancel each other out. So just be careful of the unequal amount of hydroxides and H pluses that could be given off here. Now, if you're coming from an AP chemistry land, I would never use this formula to do this. I would find the moles of the HOS. I would find the moles of base first by multiplying. Okay, but that's a different way and different story for another day. So let's go solve for this. I put the 2 down here, remind ourselves that we put how many H pluses and hydroxides, but we don't have to. And again, 90%, 95% of your problems will never have that, but you should take a look to see how many OHs per how many H pluses. They're normally going to be equal, and this could be a part 2 question. So now we're going to do our math to solve for this, okay, and this should be pretty simple. And it winds up being a simple problem. I know I'm explaining it way to death here in terms of detail, but I always want to show you the different ways that you can see this problem again. It's not always going to be presented the same way. All right, so in any case, 3 variable big M problem. So what we're going to do here is we're going to solve for this 0.3 times 100 and put this into your handy dandy calculator if you have to, no big deal. And of course, this is going to equal 30. I'm just going to put this over here and probably going to write a little smaller because that's just a big big line there. All right, as I make myself laugh. So this is 0.3 times 100 is equal to 30. So we've got equal to 30. And then we have 0.6 V, right? 0.600 V. Now we're going to solve for V. So V is the volume is equal to 30 divided by 0.600. And then we put that in our handy dandy calculator. 30 divided by 0.600. And then we get volume is equal to 50. And that'd be 50 milliliters because we started with milliliters, okay, in the proportion, and so everything would cancel out except for the milliliters. So that's why number 2 is the answer. Okay, now notice they put 25 here. Now let's think about this for a second. I know you want to move on to the next problem, so you can go on if you can, but I want you to understand how this works. If in fact this was barium hydroxide, and it is, and if this was HCl instead of H2SO4, okay, we would need double the amount of volume we had. We calculated 50 milliliters of HSO4 is needed to completely neutralize the base. Again, neutralizing the base means all the H pluses are matching up with the hydroxides to make water. If our acid was only gives off one H for the 2 bariums, wouldn't we need twice as much HCl? So the answer would have been 100 milliliters if, okay, our acid was HCl, and we would have been able to solve for that because you would have put this 2 down here and a 1 down here if it was HCl. All right, so when you solve for that, V, you would have a 2 times everything, and that's would make this to be 100. Now it's not 100 because it was an HCl. So the answer is 2. All right. And it's a classic MV equals MV problem. How do you identify acid and bases are added to each other? And there's going to be 3 variables given to 1 unknown. Okay, if you don't know the formula, table T shows you. Number 46 is 2. Number 47. Number 47, given the formula for an organic compound, carbon-based, what's the name given to the group in the box? Well, we do know, if we remember our naming system, that the first thing we'd always do is we would name the longest continuous carbon. I know they're not asking us to name the entire compound, but doing so will help us understand what they're pointing to. So we know this is 1, 2, 3, 4, 5, 6, 7. So again, if I count the other way, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. The first thing we do is find the longest continuous chain of carbons. So we found that there's a 7 carbon chain. And so the prefix is called hept. Okay, so that's a hept. And I see that there's single bonds between the carbons, and that's an ane. Now where I get the hept from is table P. Table P shows me 7 carbons. It will give me the hept, and table Q tells me the ane. Now I know I don't need that, okay? But we're going to name it anyway so we understand what they're pointing to, because you may not understand if they're pointing to the longest continuous chain or pointing to the attaching group. All right, so let's go to table P and Q for that reason. So table P tells me that if I have 7 carbons in my longest continuous chain, it's a hept. Okay, and because I saw there were single bonds between the carbons, okay, that's an alkane. Remember, the anes are for single bonds. Okay, now there was an attachment group, and there was a 2 carbon attachment group that was not part of the longest continuous chain, and that's an F for the 2 carbons. So let's go back to the problem. So I got my heptane, longest continuous chain, and then I have a 2 carbon attachment group here. Okay, so what is this 2 carbon attachment group? Well, it's an F. And what we do, and this you can't look up, you have to know this, but you know the choices are kind of giving it away. We add YL. So this is going to be an ethyl heptane. Now we don't just say ethyl, we have to say what carbon it's on. So it's on the 1, 2, 3, 4th carbon. If we count the other way, it's 1, 2, 3, 4. So this would be a 4-ethyl heptane. Okay, and that's the name of this on the 4th carbon of the longest continuous chain that is a hept. There's single bonds. Now, of course, you didn't need any of that, but you had to understand in order to know that this was the attachment group, you should be able to figure out this is the longest continuous chain. So this is an ethyl group. So if you couldn't understand any of that, you need to understand that for the regions for different problems. But this is a 2 carbon group. So table P tells us that a 2 carbon group is an eth group. Okay, and we add YL if it's an attachment group. But you can see all your choices were YL, so really all you had to know was that a 2 carbon group is an eth, and you could have figured that out. 47 is 2. Number 48. Number 48, a particle diagram question. They love these. Sometimes you have to draw them. So they give you a little key, and they want to know which type of matter is represented by the particle diagram. Well, this is basically classification of matter kind of question. And what we have is two different atoms chemically bonded. And two different atoms chemically bonded is called a compound. And how do I know it's a compound? Because compounds have fixed ratios. In this case, there's a ratio of one of these atoms to one of these atoms. Okay, for instance, HCl, hydrochloric acid, is a compound. There's a hydrogen bonded to a chlorine, and it's a 1-to-1 ratio. That's the formula. Hydrochloric acid is not H2Cl, it's not HCl2, it's HCl. What makes its properties individual or special is the 1-to-1 ratio. Now we know why, because of the bonding. So this is just a compound. Now we should know that the smallest part of a compound is a molecule. And if you notice, all of these molecules are the same. That's why this compound is considered to be a substance. Okay? And it can't be a mixture, because a mixture is going to have two or more substances. Now, what else is a substance? An element by itself. So if I was to put, let's say, a blue circle here to show that they're what? Atoms that are blue mixed up, so we would have what? A mixture of a compound and an element. Right. Okay. And there you'd have two or more substances. What's a substance? A compound. Also, a substance is an element by itself. Now, elements, and this is important, can be an atom that's hanging out by itself, or it can be a diatomic element like O2, N2, all your Hofbrinkels or Brinkelhofs. Okay, and I say, what is that if you don't know? I call them Hofbrinkels, but people call them Brinkelhofs. Hof, Brinkel. I'm just going all the possibilities. And these guys all can be what? Diatomic, H2, O2, F2, Br2, I2, N2, Cl2. So these are called elements as well. Okay, so this can't be a mixture, because we only see, in this case, even though I've added to it, only one type of substance. And it's homogeneous because it's made of the same type of molecules with a fixed ratio. And elements are a substance because they're homogeneous, because they're made of the same type of atoms that we know make them the same based upon the number of protons. Okay, that's why number 2 is the answer. So number 49, which substance is an electrolyte? Woo, it's an electrolyte. Electrolytes are compounds that break apart into ions in solution. And this is important. So let's say I have a solution that has positive and negative ions. Here's my positives, equally interspersed with my negatives, and guess what? They interact very well with the water, because water is polar. It's got positive and negative areas. So let's just say I've got a solution of positives and negatives. Now, in this solution, which has free ions, and that's the key here, to be an electrolyte, you have to have free ions. Okay? Now, if I can dissolve them, if they're aqueous, and if they're ionic, I can also heat them to their liquid. So free ions. So whether this is going to be a compound that has been dissolved, or it's been heated to the point where it's liquid ions, it's the same idea. Now, if I was to drop something like a negatively charged object, very, very negative, what's going to happen is all the positives are going to come running. Hey, I like the negatives. And the positives come running, and the negatives are going to be repelled away from that. And what you see, okay, is eventually, and if I would show you, this is what's happening, and what's going to happen, party people, is that in the very near future, very quickly, when I put this blue object, I guess, that's negatively charged, what we're going to see is all the positive ions are going to be running over to attract this negative, and all the negative ions will be left to the remaining part of the solution. So once something that was very negative on one place of the solution, now that negative has come over here. How'd that happen? Because of the free ions, the ions are able to move, okay, basically conducted the charge from this side of the beaker to what? to this side of the beaker. So a charge was conducted by the ions flowing. This is no longer negative because the positives are sort of neutralizing these negatives, and the remaining part of the solution is negative. So a charge got conducted by the positives moving, by the free ions. So what's an electrolyte? Who produces free ions? There are three things only. Number one, salts. Now what's a salt? A fancy name for ionic compound. What's an ionic compound? Normally a metal and a nonmetal. And you should know that by bonding, they transfer electrons to make positives and negatives. They exist normally as solids, so they either have to be dissolved in water or heated till they become a molten liquid to have free ions, because ionic compounds normally exist in the solid phase. Okay, because positives and negatives attract each other very strongly, their melting points are really high. Okay, second thing that produces free ions are acids. Acids dissociate, okay, like HCl, into, guess what, H plus ions, which make it an acid, and its conjugate base, the Cl negative ion, or anything that could be the other part of the acid. And of course, the other electrolyte is a base. A base is really a fancy salt, usually like NaOH, that when dissociates in water to Na plus and OH minus. So the bottom line is that we have to have free ions, and these are the three different things that do that. So we're looking for something that's either a salt, acid, or a base. So we look at choice one. Well, this is called a molecular compound. The oxygen is what? Covalently bonded. It's sharing electrons. And sharing electrons is non-electrolyte because these guys do not dissociate into ions. Things that are covalently bonded, made of what? Non-metal, never break apart into ions except for one small case, and that is organic acids, the Cu group. Okay, so this isn't going to work. C3H8 is a hydrocarbon, and this hydrocarbon, okay, never dissociates because guess what? This is bonded covalently, okay, between what? Nonmetals. So that is non-electrolyte. This is a noble gas that doesn't bond to anything, so it doesn't make any compound that's a salt, acid, or a base. So we're left with choice 4 as the answer, and because potassium nitrate is a salt, it is ionic. KNO3 party people. This what the heck is that cluster from table E is a polyatomic ion. So in water, it breaks apart into K plus and NO3 minus. Look at that, free ions. So in this case, they gave you a salt. They gave you one ionic compound out of two molecular compounds in one element. Why they call these molecular? Things that are covalent make molecules, and they're bonded covalently. They're sharing electrons. They share electrons because they both have high electronegativity as nonmetals, and therefore they never pull apart as ions. Nobody's strong enough as a covalent bond to rip electrons away from each other to make an ion. But when you have a metal who holds on to electrons loosely, attached to a nonmetal or in close proximity to a nonmetal who pulls electrons away so aggressively because their difference in electronegativity is so great, you will have negative ions for the nonmetal and positive ions for the metal in those compounds, and they'll dissociate into those charges when they're in water or they're liquefied by heat. So that's important to know. 49 is 4. But again, there is an organic what? Acid out there that loves to be this answer, and it's that Cu group. So if you see a Cu group that's covalently bonded, that's the exception to molecular compounds, because guess what? In table R, it's an acid. Okay, so 49 is choice 4. Number 50, which type of organic reaction produces both water and carbon dioxide? And it's combustion. You've probably been talking about combustion all year long. You take some carbon-based fuel that's a fossil fuel, because past living things have carbon. You add oxygen to them. Of course, this has H's too in some number, so all the carbon reacts with the oxygen to make CO2, and all the H's react with the O to make water. And so CO2 and water are very stable compounds, so these types of reactions are very exothermic. These reactions, remember this is the energy of the reactants, the hydrocarbon, which is CH and O, and this would be the products. And CO2 and water are very stable. They stay around. They have to because we need water for life, and CO2 has to get back to the plant to reproduce oxygen. So these reactants are very unstable, and the products are very stable. So therefore, the difference of where you start and where you finish is our delta H. Remember that enthalpy, the change in heat, and because you're going down, delta H is negative, which means exothermic and the energy is here. There's a place to look to remind yourself what combustion is. Let's go there. So top of table I, look at here, party people, this is all combustion. Okay, look at delta H is negative. It's exothermic. Carbon-based fuels, methane. This is propane. This is the gas that's in your barbecue. Okay, plus oxygen is CO2 and water. This is octane. This is gasoline. Look at the carbons. Look at the O2. Look at all of the same products, CO2. So all of this is combustion. This is methanol. This is alcohol burning, and this of course is glucose being oxidized. This is basically what your body does in a slow burn to get energy from sugars that plants give us. So this is cellular respiration right here. And notice the delta H's are all negative. So there's a place to remind yourself what combustion is. Okay, very important. And of course, in the bottom of table I, if you forget, they tell you that the minus sign indicates an exothermic reaction. So 50 is 2. Now, you have to know these other ones, okay? And if you don't, let's just quickly review those because they will pop up. Now, let's do esterification, probably the most important one, or at least the one that's troubling to most. Esterification is making an ester. And you make an ester. Now, an ester, to identify an ester, we would go to table R. And we go to table R, okay, we would see that an ester has a R to a C, double bonded to an O, to an O, to an R prime. So what you have is, this is the rest of an organic compound. This is in the middle of a compound, and these would be the rest of some carbons and H's, some carbons and H's. So what we have here is, let's do an organic acid. It's always an organic acid, a Cu group. And let's just make this CH3. And then I'm going to react that with an alcohol. Let's make this methanol. I'll do the OH here. I'm writing it kind of backwards to show how it attacks. And then put the rest of the H's here. And what happens, party people, is the water comes out. It's kind of like a dehydration synthesis, but when you react these, this is the arrow. I want to put the products over here. We're going to make water, and they're going to push these guys together. And when you do so, I'll put this back in blue, we get the carbon double bonded to the O. We have the CH3. And then we're going to put the what? This is going to be a CH2 here. Oh, I'm sorry, there's an O here. So that makes the ester. And then it makes the CH2 and then CH3. Okay, and there's your ester. There's that middle group. And of course, there's your R's. So that's what esterification is. And the key there is to remember that you're producing water. Water's coming out to make this link together. And to name an ester, which always baffles people, I always say split the O's in half. The organic acid had the what? The carbon double bonded to the O in it. So this is the O8 ending. So this is ethanoate. Okay, and then there's the alcohol group, which is a 2-carbon group, ethanoate. And I'm getting all that from table R. But just to identify that, that's esterification. Fermentation, okay, is when you think about fermentation, when we ferment sugars, we make alcohol because of anaerobic glycolysis, or a fermentation pathway. When you don't have oxygen, that some microbes, yeast, like to do that using zymase, but bottom line is you're taking some form of sugar, so C6H12O6, and they might put zymase up here, or yeast, and you're going to make what? CO2, and you're going to make ethanol, which is eth is 2 carbons. There's an OH for the alcohol group in table R, and you fill in the rest. And I believe you're going to make 2 of these. and put a 2 in front of these for these molecules. This molecule. I'm just going to say a 2 of this molecule. Okay, and that's basically what you're going to have. And sometimes the alcohol that we produce, the ethanol in wine, comes from the what? The grapes of sugar, or the sugar that comes from grapes. We make wine, that ethanol. Of course, if we can keep the CO2, that'd be champagne. Okay, we can use the sugars from grains to make to ferment and make liquor. Okay, and so that's what fermentation is. And the addition reaction is an important one. And you hear the word addition, you're going to add to a unsaturated hydrocarbon. For instance, okay, let's say you have, remember, it has to be unsaturated. All right, so let's take with here we go, this unsaturated hydrocarbon. Now, why it's unsaturated? Because it's holding less H's, because there are more bonds between the carbons. Remember, carbon must only have 4 bonds. So that's why you see I'm not writing an H here. There's 1, 2, 3, 4 already, so I can't put an H here. That'd make it 5 bonds. Same reasoning here. Now, if I want to add, let's say, Br, that's bonded to Br, it's going to attack this double bond and open it up. And when it opens it up, it's going to make these 2 carbons become single. You're going to put BRs on 2 different carbons, and now you're going to make single bonds between them. And of course, I'm going to add the other C here that's already there as H's. And notice something with addition, everything added. So you had 2 compounds, right? This is one compound, and this is the other compound. You're adding 2 compounds to make one, okay? And that's what addition would be. But of course, the answer was choice 2. So I hope that helped. Look for the link when I have it ready for the part 2, the free response section, I like to call, okay? But I think it's called part B2 and C for this test, all right? Good luck.